Check. There it is. Check one, two. There. Something. I know, but so I was at plus 27. Nothing. Check, check, check. One, two.
Okay. Hello, everyone. We're going to go ahead and get started. If we can have everybody seated. Our next speaker is going to be via Zoom. It is Dr. Patrick Reynolds. Dr. Reynolds grew up in El Paso, Texas, received his BA in biology from the University of Texas at Austin, his MD at UT Southwestern Medical School in Dallas, and his PhD from University of Texas, Austin, and his pediatrics training at the National Naval Medical Center. His postdoctoral fellowship was in cancer immunology at UT Southwestern. He holds the rank of commander in the U.S. Navy. He is currently the Pediatric Cancer Research Center Director for the School of Medicine at Texas Tech University. His research focuses on cancer developmental therapeutics, and he pioneered the development of the differentiating agent cisretinoic acid for treating childhood cancer neuroblastoma. Dr. Patrick Reynolds.
Thanks, Pat. Thank you very much for inviting me, and thank you for making Zoom available. I'm sorry I couldn't be there with you in person. Let me get these slides up and see if they're working okay. First, I'm going to get the share going. All right. Screen. Can you all see the right slides now?
Nothing yet.
Okay. It should be going on your end, so maybe, here we go. That's what I didn't click on that. Sorry about that. Now you should see them.
Yeah, we're good.
Actually, you're seeing the wrong screen, so let me redo this. Now we'll try it. That should work.
There we go.
Okay, excellent. So what Pat asked me to talk about was ATRX, and I'm going to explain to you why we're not going to talk much about ATRX, but instead we're going to talk about telomere maintenance mechanism, because ATRX is really a subset of one subset of telomere maintenance mechanisms. ATRX is this interesting gene that's a chromatin remodeling protein. The gene makes a chromatin remodeling protein. And cancers that have inactivating mutations in ATRX are almost always of the alt phenotype. We're going to talk about that phenotype. It's the alternate lengthening of telomere cancers. But conversely, there are many, many wild type ATRX non-mutated cancers that have the alt phenotype. So really, ATRX mutant neuroblastomas are a subset of alt cancers. And while some people have tried to target ATRX, since it's an activating gene, mutation, and it's a subset of these alt-positive cancers, what we really think is the dominant phenotype here is alt, which is what I want to talk to you about. But I wanted you to be aware that if there's an inactivating mutation of ATRX, it's almost always alt. That said, you can pick up mutations on ATRX that are not necessarily inactivating, and those cancers aren't alt. So, for example, when Dr. Burko is working with John Maris and I almost say, and looking at the 0532 sequencing data, trying to characterize which ones are ATRX, we finally called inactivating mutations based upon the fact we had also detected them as alt. So for that reason, I really want to focus today on telomere maintenance mechanisms for you. And you've probably heard about telomerase and the fact that some people relate it to aging, which it is related to, but it's not what causes aging, of course. It's just related. But this is this very interesting enzyme we have that it's the one reverse transcriptase. Reverse transcriptases are those enzymes that copy RNA into DNA that viruses use. Okay, and we have this on our bodies, and it's there for a couple of reasons. And one of the major reasons is because when our children start out, they need a full length of telomeres. And the reason for that is you see this in this right here. If as each cell divides, each time the cell divides, the ends of the chromosomes, we have linear DNA, bacteria have circular DNA, it just continues to replicate. But our linear DNA cannot replicate the last few pieces of it as with cell divides. So each time a cell divides, you're going to shorten that DNA, okay, unless you make it extended at the end. And that's what telomerase does and what telomeres are. Telomeres are these caps on the ends of the chromosomes, and the telomerase puts a nonsense repeated segment of DNA on there that basically protects the rest of the genome, allows the cell to divide and shorten that without compromising the genomic material and information that's contained within the rest of the chromosome right in here. And it does that by copying an RNA template to make the last strand of DNA. So it was able to extend the DNA at the end there. And we have most of our cells inactivate that, and it's probably a mechanism of protecting from cancer, because as these things erode, you then eventually get to the point where the cell gets senescent and involutes. So if a cell starts growing out of control, the telomerase not being there will allow the cell to basically not get out of control, not continue to grow. So in some ways, this is an early mechanism we had of protecting against cancer, of not having telomerase on in all our cells. Of course, it's on in the germ cells because you don't want to start out life with a short run of telomeres. So we all get the nice long telomeres from our parents due to the germ cells having the telomerase present. But it's also some cells have to divide, for example, hematopoietic stem cells. So they have reactivated telomerase and use it. And so it is not a cancer-specific gene. It was thought you could target this and get rid of cancer cells, but unfortunately, it's also needed for certain germs, not our germ cells, but our stem cells within the body. Now, there are cancer cells that don't make telomerase. Now, about 85% of them do, and in case of neuroblastoma, it's about 70% that have high telomerase activity in the high-risk neuroblastomas. A lot less than the low-risk neuroblastomas, but in high-risk neuroblastomas, about 70% of them will have telomerase, and I'll show you those data. But there is this group of cancers that will continue to grow and are lethal that have no telomerase. And we first observed that actually in neuroblastoma cell lines many, many years ago. Tried to publish it, nobody believed it. So we gave up for a while, eventually published it after a very bright physician that's working on this in Australia by the name of Roger Reddle started characterizing this alternate lengthening of telomeres and making people believe that it exists. And essentially what this is a cancer-specific mechanism where, and it's not well understood, but it's basically a DNA repair mechanism that's turned on by the cancer cells that allow them to make their telomeres. And when they do this, they end up making telomeres that are, some of them are short and some of them are long. So you get this very heterogeneous picture in these tumors. And as you'll see when I tell the story of how we got into it with neuroblastoma, we sort of suspected it was there, but it was the first study I'll show you where we really understood about it. Once we did that, we learned that of high-risk neuroblastomas, 23% of them have this phenotype. So that's not a small number of these high-risk neuroblastomas. And it's present in a lot of other pediatric cancers. For example, pediatric high gliomas, a very troublesome, difficult to treat cancer. 40% of those are alt, and 71% of osteogenic sarcomas have the alt phenotype. So it is prevalent. If you look across pediatric cancers and take it as just a subset, it's a larger subset than any single pediatric solid tumor if you add it all up. Now there's a third group of these, and we'll show you the data on that. And these are ones that don't have any telomere maintenance mechanism that we can detect. And this may be because there's a mechanism that we don't have the techniques to detect yet. But in neuroblastoma, we think that a lot of these do not have a ability to make telomeres. And it's about 6 or 7% of high-risk neuroblastomas fall in this group. And most of low-risk and intermediate-risk neuroblastomas fall in that group. And I think the most classic example of this are stage 4S patients. Those patients, the infants that have metastatic neuroblastoma, that clinically we've been able to identify them. They commonly can spontaneously regress with no therapy whatsoever. And this was discovered as being related to telomerase by a pediatric surgeon by the name of Eiso Hiyama in Hiroshima. And Eiso did this beautiful experiments because he was serially biopsying these patients where he looked at telomerase and telomeres, and he showed what really happens in 4S neuroblastoma spontaneous regression is that the telomeres shorten. They shorten down to the point where eventually the cancer just involutes and goes away. So there is some of these patients, as you'll see, that are not 4S, and we're starting to identify them in studies with the Children's Oncology Group. Now, why do we care about this alt mechanism? Well, one reason is because, and this is from a paper that Balakona, who's now in our faculty, was a graduate student when he did this in my lab, looked at this, and these are large numbers of neuroblastoma cell lines within the COG repository who are characterizing their survival fraction when they're treated with SN38, which is the active metabolite of irinotecan or topotecan, etoposide, 4-HC, the active metabolite of cyclophosphamide, another drug we treat neuroblastoma with, melphalan or carboplatin. And as you see across here, there's a range of sensitivities, as we've always known, for these drugs in most neuroblastoma cell lines. But the alt cancer cell lines, you look up there, the survival fractions are very high. They're extremely resistant to chemotherapy. We had several of these that we'd established that were alt and verified they were alt. And that's what this experiment shows. And this is true for the combinations such as cyclophosphamide plus topotecan or temozolomide or irinotecan. So this is a very drug-resistant phenotype, and as you'll see, that's not surprising that they haven't done well clinically. We see the same thing if we put these alt and non-alt, in other words, telomerase positive neuroblastoma xenografts into nude mice and treat them with temozolomide and irinotecan. The survival of the mice with the alt cancers is much lower than, and we don't see any of them make it. Whereas we can see long-term survival of some and certainly better survival for the telomerase positive neuroblastoma xenografts. So it's a very drug-resistant phenotype. And the way we detect this, there are several ways you can detect it, but there's some that are more amenable to clinical application than others. And this C-circle assay, which was developed by the Australians, is what we found to be the best way to pick these up. What happens is, and this is something Roger Reddle described a number of years ago, that these alt cancer cells have these extra chromosomal telomeric repeats. This is the telomere DNA sequence that you see on the ends of chromosomes, but it's not on the chromosomes. It's in this circular plasmid-like, sort of like a bacterial genome that's floating around in the cancer cells in as many as 1,000 copies in these alt cells. And we don't know whether this is a byproduct of how they make telomeres in alt cancers or if it's how they make it. It's still poorly understood exactly what its role is. But what's interesting about it is that it's partially double-stranded, so it's self-priming. So that means you can take this enzyme, which will will not amplify linear DNA, okay, DNA like in normal cells, but these structures can get amplified with this 529 polymerase. And so when you first amplify that with this, then if you run a PCR to detect telomeres, what you get is this, you have the control where you haven't used the 529, and then you have the 529 treated ones, and you get a much quicker signal out of the PCR assay for the ones where the 529 is exposed. So this gives us a positive result. So we see this is alt. And then if you run a non-alt cancer, you don't see that amplification at all. So that's the basis of this assay, and it's incredibly specific and sensitive. And so we've used that and gone in and looked at a number of different, and we'll show you some of these data from the Children's Oncology Group, a number of patients, a large number of them actually, and come up with this schema for classifying tumors by telomere maintenance mechanisms, where we have, if it's highly C-circle positive, that's going to be alt positive, and if you see C-circles, that's it. You know you've got it, and those are classified as alt positive. Whereas if you have high expression of the TERT gene, you classify those telomerase positive. And we virtually never have both of these at the same time, and if we do, we have ways to work that out. But these are mostly mutually exclusive, and if you have high expression of TERT, which is the gene coding for telomerase, then you've got telomerase positive. And then you've got this group in the middle where we can't find either of those. And to really rule out that they have a telomere maintenance mechanism, we go through several other assays. The UTF assay is a staining assay to look at telomeres on sections that's labor intensive. And then we look at the enzymatic assay for telomerase, which is a very sensitive way of doing it. It's also labor intensive. But once we go through all this, we can, if we don't find either of these positive, then we can classify these patients as having tumors that are negative for any known telomerase maintenance mechanism. And so that's the scheme that we've been using in the Children's Oncology Group to look at these. When we first did this, the first question we had came back to ATRX. We had been working with Bill Fisher, who's at a pancreatic surgeon I work with at Baylor, looking at pancreatic neuroectodermal tumors. It's if you will, one of the adult variants of neuroblastoma to some degree. It's a neuroectodermal tumor that's aggressive in adults, occurs in the pancreas, and they have a high incidence of alt. And we started looking at them with him, and they were a lot of them that were ATRX wild type. They weren't mutant for ATRX. So I talked to John Maris and the group that was doing the TCGA work at the NCI had a bunch of COG samples that were being sequenced, and I said, can we look at the DNA from those? And we did, and compared it to our sequencing, and found exactly the same thing, that almost half of them were not ATRX mutant. But then we decided to extend this, since we had that DNA, and we also were able to look at the RNA expression of TERT gene, the telomerase gene, and then look at the outcome for these patients. And as others had reported, the telomerase positive patients had lower survival, and take these survival numbers with a grain of salt for today, because this is much older data. So a lot of these patients were not treated the same way they are treated today, but they're all high-risk patients. And when we looked at the C circles in these, they certainly did not do well, but we were not seeing any significant difference between those. And of course, the majority of these are telomerase positive here that were in this group that were non-C circle positive. But when we combined the two together, that's when we saw something very interesting. And that was the telomerase positive patients progress faster. And in those days, this is about the floor we had. We're now, of course, much higher in terms of our overall survival for high-risk neuroblastoma. And we saw the slower progression, which we anticipated, because all was known to just that these cancer cells are somewhat indolent, but relentlessly progressive. And in this study, they came out about the same as telomerase positive. As you'll see, it's no longer true. And then we had this interesting group that we couldn't detect any telomerase maintenance mechanism on, and their survival was significantly higher in this study from the others. So that's when we came up with the concept of these three different groups as being the major groups: the telomerase positive, the alt positive, and telomere maintenance negative. And the COG wanted to confirm this. So they had just completed this study that many of you know about, that Julie Park led, which was a randomized study randomizing patients to get single courses of myeloablative therapy with stem cell transplant or single transplant to 2 sequential courses, which significantly showed a significant outcome improvement for these patients, especially if they got maintenance immunotherapy after completing the myeloablative therapy. And so COG sent us as many of the DNA and RNA from as many of these tumors as they could. And we saw the same pattern here, although this is what we kind of expected was going to be the case. The alt patients now were doing worse for all the patients in this study than were the telomerase positive ones, which are now we're getting more effective therapy than we were in our earlier study with the TCGA. And so there was a significant difference between these. And although it was smaller numbers of patients, so it's not significant, there's this apparent better outcome for these patients that have no telomere maintenance mechanism. And as we get more patients, I think we'll confirm that this is significantly different, that if we can identify that group, then they are probably going to do quite well relative to the other 2 groups. The statistics on this were challenging because look at these curves cross over, and that drives statisticians crazy, but Arlene Naranjo at Statisticians COG worked this out quite well, and there's techniques to deal with that. But it also tells us exactly what we've seen before, and that the telomerase positive neuroblastomas progress more rapidly than do the alt neuroblastomas, but they also are the ones that then respond to therapy and eventually get long-term disease-free survival better than the alts, which progress slower but continue to progress, and you come out with a lower survival with that group. When we did this, we had a hypothesis, and that was that this was the group that was really benefiting from the tandem transplant randomization, this group that had telomerase positive, and that the alt were so highly drug resistant that they wouldn't benefit much from it, which this data looked like. But we were absolutely astounded when we looked at the randomized question. So here is that study, the Park study, the 0532, looking at just the alt positive tumors. This is all the patients that were randomized that we had tumor to analyze. And then we also did a study analysis where we just looked at those patients not all the patients on the study got anti-GD2 immunotherapy afterwards. And then we limited it to those that did. This is where the data got really, really striking. Here's the single transplant patients that got treated with one single transplant, and they're all alt on this. And we're down below 20% on this 8-year overall survival curve. Whereas look at, we're well north of 70% here as a plateau for these patients that got treated with tandem transplant. We see the same thing for all patients, so it's not just an artifact of having the immunotherapy in there, but the immunotherapy does seem to significantly improve those, as we expect it to. And so this really calls into question whether or not these patients absolutely need a tandem transplant. And to confirm that, we're looking at all the patients on the most recently completed study, although there's an arm still open, but the majority of the randomizations are completed for ANLB 1531, the study the COG completed a little bit ago. And once that clinical data is released, we'll be able to look, since all the patients on that study got tandem transplant, if we're seeing curves that look like this for the alt patients, then that will confirm that this, as we see here in this randomized study, is true. And this looks like what we need to be treating patients that have these tumors with, is tandem transplant for sure. So I wanted to talk a little bit about something that I think is exciting for detecting these that we're working on, and that is, as I showed you, it's kind of challenging looking at the tumors for these because there's a lot of repeat assays one has to do. We started adapting this cell-free DNA assay, the C-circle assay, to cell-free DNA, and we can extract the cfDNA from plasma, and a lot of that's being done for sequencing now. So Brian Crompton has extracted cfDNA from a large number of patients on that 1531 study there at Harvard, and the COG and the NCI blessed us getting some of those samples. So we got in a large number of them recently, and we're working through that with this same assay that we have that I showed you for detecting alt, and it works extremely well with plasma cfDNA. In fact, it seems to be more specific and it's very sensitive. So we're hoping that we'll actually be able to pick this up from a plasma assay, and that will be beneficial for a number of reasons. One of which is because there are some drugs coming down the pike that are very highly active against all cancers. None of them are in clinical trials for neuroblastoma yet, but we have the first one is in actually a phase 1 in pediatric trichogliomas, which is AstraZeneca's ATM kinase inhibitor. And there are some other drugs that we and others have identified that work extremely well for all cancers. And so being able to pick up these patients with a cfDNA assay, I think will be very useful. It wouldn't require a biopsy, of course, to detect that they have that kind of a cancer. And the NANT is now going to start collecting plasma in a way that we can do this assay. So we'll be able to look at this for patients that are enrolled on the NANT biology study. I think it'll be very useful. So the current studies, just to recap, TMM is being defined for the ANLB 1531 phase 3 study, and I think that's going to confirm 0532 results. But we're validating the C-circle assay with samples from ANLB 1531, which is in progress, and for the plasma test. And as I mentioned, there are investigational drugs that they're not yet ready for neuroblastoma, but they have very high activity against all positive cancers, and they're undergoing preclinical testing, and some are already now in the phase 1 pediatric trial. So we're very excited about the potential for these because alt is a cancer-specific mechanism. To summarize the talk, we have neuroblastomas that do have HRX inactivating mutations, and they're almost always alt positive, but alt is the dominant phenotype. HRX mutant cancers are a subset of those, and as best we can tell, they do not appear to be different in terms of what we could do from either prognosis or therapy with those relative to detecting the alt mechanism. The data from that ANLB 0532 phase 3 study indicate that ASCT in a tandem setting where we give 2 of these is a significant improvement for survival of alt positive neuroblastoma patients. And we're going to confirm those to also confirm what the alt data looks like in that particular study. And this work was done with a whole variety of people. Bala Konaru did a lot of the work that I showed you there, and there's a whole bunch of people in my lab working on it now, as well as collaborators we have across the COG, our collaborators at CHOP, and some interesting collaborators that I list here. These are dog veterinarians, and we're about to do some dog studies with one of the alt-specific drugs. It's something we're very excited about because dogs do get some cancers that look a lot like pediatric cancers. Unfortunately, not neuroblastoma would be a great model, but there are some for brain tumors and osteogenic sarcoma that makes for a very interesting model. So I think I will stop there and see if I can unshare the screen. Sure, I'm going to turn off sharing. Do you have any questions?
Anyone want to ask some questions here? Anyone? Oh. All right. We don't have questions for you, Pat.
Okay.
All right.
Well then,
Thank you very much for the presentation. We appreciate it.
have a great meeting.
Okay.
Guys, good to see you, Pat. Bye-bye.
Thank you. Okay. Our next speaker is Dr. Shah. He's an associate professor and attending physician at Nationwide Children's Hospital and the Ohio State University College of Medicine in Columbus, Ohio. In addition to his clinical efforts on the embryonal team in the Division of HEMONC, BMT, he is also the co-director of the Cancer Genetics Program in the Office of Precision Oncology. His current efforts include the repurposing of novel therapeutics for childhood cancers, including neuroblastoma, and the development of multi-stakeholder structure to optimize such efforts. Dr. Shah.
Good morning, everyone. Thanks for having me back. If you scroll way through the library, you'll see someone who resembles me with a lot less hair in 2014. Carrie's done a great job of representing us. My career has gone through some interesting trajectories since then, into stuff that I'm really excited to talk about. I left a lot of time for questions at the end, and I also do want to talk about kind of the design of our study and some of the other work that I'm doing in that way too. But we'll start with kind of the harder science first. So, the experience of cabozantinib for extended disease control in neuroblastoma. These are my conflicts. I have relationships with these companies. None of these are going to impact the discussion of the work today. The big takeaways from at the end, hopefully you'll have understood that we all know that relapsed refractory neuroblastoma remains a major challenge to keep in remission, and there are a lot of factors there: tumor immune microenvironment, heterogeneity, and disease evolution. This drug, cabozantinib, some people call it Cabo, some people call it Cabo. It's an oral tyrosine kinase inhibitor, and I'll kind of walk through what that is. And it suppresses multiple cancer-driving pathways in childhood cancers that include neuroblastoma. And the data that I'm going to show you today, early clinical use from off-label use in a clinical trial, support that it may have a role in maintaining disease control on neuroblastoma, but we need to know more. So again, you all know the challenges that we have with neuroblastoma. It's a heterogeneous disease. And there isn't a single therapeutically targetable oncogenic driver necessarily in that way. Some of the things that we hit are associated with the disease, certainly like GD2, but it's not the thing that's really making it be a cancer, unlike in a lot of adult cancers. In relapse, the neuroblastoma evolves and it keeps evolving and adapts to therapies. It just kind of, it keeps moving around. And it can result in multiple clonal populations, so it can get to a point where you're actually not treating one disease anymore in some patients. Current therapies can control disease burden, but they don't consistently prevent recurrence, and particularly after a prior relapse. We kind of know this. We can play whack-a-mole in the setting of relapse. We can get patients into remission, but keeping them in remission is the challenge. And tumor microenvironment plays a major role in this therapeutic resistance, and that's a whole talk in and of itself. But it's the metaphor I always use is the Death Star, and the shields are up, and we got to bring those shields down. How do we do that so that we can send someone to find that event and blow it up? So, all right. So Cabo. So what is this drug? It's a multi-targeted tyrosine kinase inhibitor. So that means it's a little molecule that will find these different receptors on the surface of the cells. And this is how the cells communicate with each other within the tumor, with kind of sending the signals out for what the tumor needs, and then communicating with the rest of the body as well to allow the tumor to survive. And so that's what these kinase inhibitors are, and that's one of many different types of proteins on the surface of these cells. And when we say we're multi-targeted, Some cases, we design those drugs to really be focused on one specific receptor as much as possible, or one or two. And cabozantinib is kind of inherently hitting a lot of these. There's some pluses to that. There's some obviously some minuses to that as well, and we'll talk about that as we talk about the clinical data. But some of these pathways, it's inhibiting new blood vessel growth. Any new tumor has to get a pipeline. It has to get a food source. It hits these pathways, VEGFR2, AXL, and TEC. It hits proliferation and hypoxia responses. So these are the things that are on the surface of the cells that say, keep growing, keep growing, keep growing. And whenever the engineer calls back and says, we can't do more, Captain, and so then it says, it's okay, keep pushing through. Doesn't matter, have enough oxygen, we'll adapt. And so we need to suppress that. And it also has evidence that cabo has effects on the tumor microenvironment. Again, bringing those shields down, or at least disorganizing them so that other therapies can be more effective. So there had been preclinical evidence. Different labs had shown that neuroblastoma can have effect against different models of neuroblastoma, in vitro and in vivo, and these are kind of the publications, including more recent publications there too. So there's a justification for having a role in neuroblastoma. We started using cabo in other patients, frankly. Bless you. We had a couple of patients with a different type of disease, a renal cell carcinoma in kids, and we had great response in that way. And again, seeing the preclinical data, it said, well, maybe this can be similarly useful in some of our patients. And so we read up our experience in 2020, and we had 4 patients at that point. There were 2 patients that were in their second remission. They had been in a state of disease control, relapsed. We got them back into a complete response. But again, we knew like their risk of it coming back was very high. So we put them on cabo between 6 to 12 months. And then those 2 patients continue to remain in remission to date. We had 2 other patients who had active disease. And so, they kind of blown through other things, or we'd gotten them to a stable disease point with chemotherapy, chemoimmunotherapy, but hadn't cleared their disease. And so then we put them on cabo. And the goal here again is let's give you a drug that's oral, and we'll talk through the risks and benefits there, but to go with the benefits of it not being particularly immunosuppressive. And in each of those cases, we had at least 6 months of disease control in those patients with good quality of life at home as well. After that report, we have continued to use it here and there, and we had 3 additional patients in particular where we used it post-relapse. And one of those had 3 months of treatment, but remained in remission for 4 years. The other had 6 months of treatment, and they remain in remission now as well. So it suggested a potential role there. In parallel, cabo was being studied in other pediatric solid tumors, had a lot of excitement in bone tumors, in particular osteosarcoma and Ewing sarcoma as well. So kind of led us to our hypothesis that cabo can be used for up to 1 year after achieving disease control. Doesn't have to mean complete response, just have to get it to a point of stability. And it could improve that 1 year progression-free survival to greater than 45% in patients with ultra-high risk pediatric cancers. And we're using this term of ultra-high risk, which actually borrowed from the good Dr. Morgenstern back there, of a 25% 1 year PFS. So. And that the goal there is to achieve stable disease or better. This is in patients for whom we've achieved stable disease or better. So. So I had the good fortune to present this data at ASCO earlier this year in June, so kind of borrowing those slides there. So this is the method of the trial. So the trial is fairly straightforward. You have to have completed all your prior therapy, and 4 weeks after the end of your prior therapy, have scans showing you're still in remission. And then you're eligible to come onto trial. We have, because the trial is still open, we have 4 strata there. Stratum A is the relapsed refractory solid tumor cohort, and that's one of our neuroblastoma patients are fitting there. So we're also studying it in Ewing sarcoma, osteo, and Redwood-Meyer sarcoma at the end of frontline therapy. We're not going to talk about that today, but that continues to enroll. So treatment itself is straightforward. When we originally designed the study, that's the other luxury with cabo, is that this is a drug that had been studied in kids specifically. It had gone through a phase 1 and a phase 2 through COG. So we knew what a maximally tolerated dose was and what the recommended phase 2 dose is. That's what that RP2D is. And so we would start patients at that dose, and that was 40 milligrams per meter squared per day. So for kind of a full-size teenager, that meant 60 milligrams once daily. So 1 pill once a day. Does have to be on an empty stomach, so no food for 1 hour before or 2 hours after, but that was pretty manageable. Time of day didn't matter. And that's one of the interesting things about this drug, is that its half-life is very long. It's about somewhere between 55 to as great as 110 hours, which means 2 weeks after you stop taking it, it's just leaving your body. And so we could be clever with the dosing in that way. On the trial, patients have to be able to swallow a tablet. Our preclinical, off-label use, our case series, we had found a recipe to be able to crush and resuspend the drug. But for different regulatory reasons, we couldn't offer that on the study itself. But that data showed even when you crush and resuspend, it was absorbed and it did have benefits. So. Treatment was for 365 days until progression or withdrawal from treatment. So if a patient has to pause treatment for any reason, that clock doesn't stop, we just roll for 1 year. There's a couple different reasons why we picked 1 year, and we can talk about the end if you'd like. So. And then what we wanted to really look at was we want a drug that isn't just safe, but it's also tolerable. And so we wanted to really be mindful of, okay, what's the impacts to patients? And so if there was what we call a grade 3 adverse event, if there was a safety event that made it, not safe for patients to continue, we would pause, or if it was severe enough, we would stop the treatment altogether. However, if it was intolerable, if the patients just didn't feel like how they were feeling on the drug, then we could do voluntary dose reductions in those way. And then we're also collecting patient-reported outcomes. So we're quantifying, okay, how do patients feel being on this? Again, that primary outcome measure is that 1 year progression-free survival. And in all of that lovely jargon there, the key summary was that of our first 18 patients, we needed 5 to make it to the end of that 1 year to show that we had benefit. And then, again, multiple secondary outcomes that we're measuring there. And so in this, still very small font, apologies. This walks us through kind of the data presented. Again, we presented in our first 28 patients, and we had a good representation across different patient types. For neuroblastoma, at this time, in June, the cutoff in March, we had 4 patients who were on study. So. For all of our patients, this is that 1 year progression-free survival, and at 1 year, the survival is actually estimated to be about 70%. You can see that as the curve keeps going, there are patients who relapse, and we'll kind of talk through what that looks like and what those different types of patients are. But it was encouraging that at least that signal there. So this is what we call a Swimmer's plot. So it's literally each patient as they go along on their journey, and what does that look like? So the green bars are the patients who made it to that 1 year cutoff. That second box down, those are our neuroblastoma patients, and so those are the ones we're talk about. The blue bars mean they didn't make it to that 1 year time point. Now that could be because they had progression, and you'll see that if you look very closely, there's a little orange dot that marks that, or patients who chose to come off study or their physician brought them off study because they just couldn't tolerate it. They didn't feel it was in their best interest, and we'll talk about what some of those cases are. And then those orange bars are the patients who are still on study. We have a lot more orange bars right now. We enrolled 5 patients this month. So amongst those neuroblastoma patients, there's 4 in the middle. We had 2 patients who made it to that 1 year benchmark. The top one, who did have progression, was not in a complete response going on to the study, so we had good disease control. And it wasn't promptly after they stopped, but after a few months after they stopped, that we did see regrowth in that patient. The second patient is the patient who did come onto the study in complete remission. We'll talk about what that journey looked like for all of our patients during that time. Made it to that 1 year mark and remains in remission at this point, a couple years later or so. The third patient had significant disease burden coming out of the study. Again, it was in a state of stable response, but had other kind of factors in that way and had more toxicities as a result, requiring more dose reductions, and did progress in the treatment. And that fourth patient came off study early, just didn't like how they were making it, how it was making them feel. So it kind of gives us that range of experience for those patients. But then again, we're seeing benefit in Ewing sarcoma, osteosarcoma, and then other tumors as well. So then we come to safety and tolerability. So this slide is focused on the safety aspect. And what it really showed us is that for the vast majority of patients, the drug was safe. When we found a more significant impact to their body, it was more lab-based things. So increased ALT, we had a couple patients who decreased neutrophils. Not with an ANC less than 500, no fever neutropenia events, no one had to be admitted for any of those things, just a little bit of a lower neutrophil count as a result. This PPE thing is palmar-plantar erythrodysesthesia, it's hand-foot. So they get this rash, and what's happening is that as those blood vessels are getting squeezed by the drug, it diminishes very locally that blood supply, and so you have to keep the skin healthy. And as long as you keep it with good inflammatory control, they still feel good. But you need to kind of get rid of all that dead skin and let new skin come in that is used to a little bit of that vascular squeeze. And what was interesting about that is for most of our patients who have this PPE, which again, the treatment there is topical. It's using lotions and topical steroids to help control that inflammation. After 3 months, when that new skin comes in, as long as it hasn't broken down that skin and formed an ulcer, it stops. The PPE goes away. They don't have to keep using their lotions. They feel much better. They just have to get them through that window and be pretty aggressive about doing that. And then we have some patients with weight loss. So that's the other kind of big toxicity with this drug is appetite suppression. They don't feel a ton of nausea necessarily. They just don't feel hungry anymore. One of my families, specifically with neuroblastoma, said, he used to house a Happy Meal, and now there's a few nuggets that are left. My nurse practitioner, this was when the study was starting, the GLP-1s were just coming along, and she said, forget Ozempic, put everyone on Cabo. It is something that we can work through, and we've learned to work through as well. We'll kind of talk about some of our mitigation approaches a little bit later. Some of the other, and then aside from that, though, it was pretty well tolerated, very safe. However, then you'll see the dose reductions number there. So, 34 dose reductions. Now, this is out of 28 patients. So that meant that some patients had multiple dose reductions. And it really showed that we had to be able to be very conscientious about how we did supportive care and help with these side effects in that way. And so that was about 86% of our patients had a dose reduction at some point. Now, other data from COG and from our colleagues have shown that that first dose level reduction, that 30 milligrams per meter squared, the pharmacokinetics, the amount of drug that's in the bloodstream, it's still expected to be a beneficial level. And they've actually shown that that dose level, it hits the right targets in different models in that way. So coming down one dose level doesn't diminish the benefit of the drug, at least it wouldn't be predicted to in that way. The study needs to prove that, but our data shows that we could do that, and so it kind of led us to a change in our approach as well. Only 2 patients were removed from the study because of safety purposes, and 2 because of physician determination. Those are interesting. Like most of these types of oral drugs, you have to look for what the interactions are with other drugs and with a lot of these supportive care things. And it goes through a pathway called CYP3A4. And while THC, it does not interact with CYP3A4, CBD does. And so these 2 patients were patients who had previously been on CBD, chose to come off, and they were on it for kind of the holistic approach. It really helped them just feel like themselves again. They chose to come off so they could come onto the study. And after a couple of months, they said, we don't like how we feel anymore. So they came off of the study, went back on their CBD, and then through kind of personal communications with their doctors then prescribed the Cabo back on study, and they've been handling it safe. So we're going to talk about that experience when it comes time to publication as well, but that's what that physician determination was. So. And then we had 10 patients who voluntarily discontinued treatment, and that's where we needed to say, okay, we need to adapt because we need to make sure that this is something worth it to the patients. So I'll talk that through. Limitations of a study like this: it's a single-arm, open-label study. We're doing a historical control. There's no stratification by disease, so we're kind of grouping these different diseases. But that's really the rationale. This is a drug that should really work across diseases, and so that's what we said. Let's look at them all together from an analytical way and from a pragmatic way. Would have loved to have done this as a standalone neuroblastoma study, and that's in fact how I wrote it in the first place. But from a number standpoint, that would have been probably a decade-long study, unfortunately. So We didn't stratify based on their prior response. We will do some of that in the analysis afterwards. And then we've had limited follow-up up to this date. We opened to enrollment on January 1st of 2022, so still a lot of good data to get there. So, all right. So then our takeaways again, we show that there's that potential to hit our benchmark, our benefit in improvement of that progression-free survival. It's safe, but it wasn't necessarily well tolerated. So this is what we did. We had been starting all the patients at that 40 milligrams per meter squared per day. We just said, everyone's ending up at 30, let's start at 30. And if after a month or two, you're tolerating it, you can talk with your physician, and if you want to go up to the 40, you can go up to the 40. And so having seen that, we're not seeing as many disenrollments, we're seeing it much more tolerable in that way. Things that we do have to watch for. So in addition to the hand-foot syndrome that I mentioned and that appetite suppression, it impacts the thyroid. A lot of the drugs in this class can suppress the thyroid in that way. And I think that it kicks in a lot earlier in that way. We've become very good at assessing if a patient is hypothyroid. The strongest marker is the patient taking cabozantinib. The little joke there. But we want to be attentive to the impacts on the thyroid that way, and replacing with levothyroxine with Synthroid where we need to. Our adolescents seem to be a little bit more sensitive from a GI standpoint, and there is concern for diarrhea, and that can range from kind of just looser stools to more significant diarrhea in that way. Our smaller kids don't have so much of that. It's really the appetite suppression that you have to watch for in them. And then there's some laboratory things that we have to watch for. There's potential impact on the pancreas. The only time we ran into that was a patient had a concurrent stomach bug, and then had a little bit of bump in their labs. They felt fine. It was just a bump in their labs. So, and then there's what I call the cabo gray. So we see that in two ways. One, with that vascular squeeze, the capillary supply to the skin is also a little bit kind of diminished in that way. So, they're not anemic. In fact, actually, the patients on study, if they had anemia, it tends to resolve pretty quickly. And it's partly in response to this vascular squeeze, but they just look gaunt, and so they just kind of can look very washed out. It's not impacting them from an energy standpoint or anything else. And the other one is the impact on hair, so it can lighten the hair. In some patients, that means they kind of go all white. Some patients, it's salt and pepper, or just at the ends. We had a couple who kind of got the distinguished senator streaks in that way. And we had one patient who was really looking forward to having all white hair, so there was a blank slate, so she could dye it whatever color she wanted, and she had no impact on her hair color at all. So, and then I said, you can just dye your hair. She's like, oh yeah. So then, again, doesn't hurt them. And when the study's done, for most of our patients, all of that has resolved. The thyroid resolves. Again, our neuroblastoma patients are at risk of hypothyroid, so there's that existing background there. But the skin changes, the hair changes, the appetite, the GI impact, all that really resolves in that way. So again, here's kind of that front overview that I had. The other thing I want to emphasize about the study is we really wanted to design it to be as least impactful and as broadly available to patients as possible. And so it wasn't quite a decentralized study. It's run out of our consortium that's based in Columbus, Ohio, but we're open at 5 sites right now, at Montefiore, DC, Primary Children's, Colorado, and at UAB. And then we're opening at MD Anderson. We're just in that final contract stage. And even there, we really wanted to make it accessible to patients outside of those sites. So we have our dedicated time points where patients have to be seen and evaluated, but this is what we call FDA exempt. So that allowed us to be a little bit flexible. So scans can be done at your home institution. Have to be done in the right time window so that whenever you're seen back at our institution, we can kind of align all the data in that way. Labs, in theory, could even be done in that way. We've been approached by some people about international patients, and we're open to that. We haven't had that opportunity yet, but there's no reason why that wouldn't be allowed in that way. And we really try to partner with that home doc for a lot of these side effects in that way. So the first 3 months, we use 4-week blocks technically, but for the first kind of 3 cycles, we do have the patients coming back to wherever they enrolled, that local site first. To keep an eye on drug levels, everything like that. And then we see that's our first tumor measurement standpoint, is that 12-mark benchmark. But if you're tolerating the drug at that point and the scans look good, then we space it out. So then you're only coming back to the local site every 12 weeks after that. So we really try to kind of limit the extent there. Because of the half-life of the drug, we have some flexibility with some of these other labs that we want to get, like pharmacokinetics. So you may have had your kids on studies where like, oh, we have to get a lab, 1 hour after, 2 hours after, 4 hours after, things like that. We don't have that limit in that way. We are getting additional blood samples for later analysis, things like that. So we want to be flexible in that way. But and the reason why I'm highlighting a lot of those is that we had a couple questions that were very savvy questions yesterday about, have anyone looked at how patients at big centers do compare to patients at smaller centers? Or, if you have a toxicity with a drug, should you go to the originating institution to get treated after that? And I think that question is upside down. It's not the big centers do better, so all patients should be treated there. It's just not tenable. I highly respect and love working with my colleagues at those big centers. And we try to think of Nationwide in that same group because we are a big institution. We have lots of capabilities. But patients shouldn't have to schlep to Manhattan, LA, DC, Columbus for their care. We should be figuring out how to get that out to other sites. And so we have to kind of be looking at decentralized approaches, other approaches where, again, we're making sure that we have safety. This isn't for phase ones necessarily, but for when we know what to look for, how do we partner with your local institutions, get more of those patients on? You guys are a testament to what you're doing for your kiddos, but that we don't have every family here, and there are limitations, and it's, everything about your life shouldn't mean that you should have to uproot your life for 18 plus months at frontline therapy to get your kids high quality care. So just wanted to plug that in. So that's what I got, and lots of time, so happy to take questions about this or really anything that's been discussed.
Thank you, Dr. Shah. Anyone have questions?
In terms of stable disease, how do you guys determine that to be qualified for the study?
Sure thing. I'm sorry. I did want to ask, if you ask a question, if you can just say your name.
Hi, I'm Brittany Super.
Hi, Brittany. So for stable disease, so again, the short answer is radiographic generally. So we look at the scans that you had when you started your most recent therapy. So if it's a frontline for those other strata, but for our relapse refractory patients, at the time of relapse, we want to see what your disease burden was there. And so if you had measurable disease, something we could see on a CT or an MRI, then we need to repeat that. If you had only what we call evaluable disease, you could see it on an MIBG scan or a PET scan, but you couldn't measure it out, then we'll need to repeat that. If you had marrow disease, we need to make sure we cleared out the marrow disease. And so then that's where timing is important. And so we want to get the eligible scans at least 4 weeks after the end of your therapy. Because we don't want to pick up patients who are just kind of under control. And we know for some of these other tumors in particular, you can see you stop therapy and 5 weeks later they're already relapsing in that way. So we had to make kind of the criteria be a little bit more broadly applicable in that way. You're eligible for up to 12 weeks after, so there's a window there. We want to enroll patients within 2 weeks of those qualifying scans. If you meet kind of all the other criteria, but we don't hit that benchmark, we do have a little bit of funding in the study to be able to get a second set of research scans if we need to. So.
Daniel?
Pat, am I allowed? Yes, breaking the rules.
You are.
Hi, I'm Daniel.
Hi.
This is really challenging, these studies in the maintenance setting. I just wondered if you could kind of discuss, we kind of get to the conclusion of more data are needed. And the question is, how do we actually get to the point of getting those more data? Because, this is really difficult area to demonstrate that the drug is effective because, you've not got disease that you can see shrinking away. Often you've got patients who are in remission. And I just wonder if you could comment on how will we take this or other drugs forward to actually know, is it definitely working or not, given the challenges of that?
Yeah, no, great point. For me, the more data is needed because we're in the middle of the study. And I want to make it clear that it's always kind of that balance of, I don't want to be saying, what's good for me is not for thee. I used it off-label at the start because I didn't have a study. Now we have a study, we should try to organize as much as possible. That's kind of where that more data was needed. A lot of the correlatives that I skimmed over go to that point. So we're collecting ctDNA at multiple time points in that way. We're collecting PKs, we're collecting plasma, because we know there'll be questions at the end that we don't know were going to be questions when we started the study. So exploratory tube. So, and then we have histology as well. So we're requesting blocks. Now, obviously, we'd prefer to have the block at the time of relapse. In some cases, we're having to take archival samples instead. So we'll be able to get some signal. Now, is it going to be powered in that way? Likely not, but we'll hopefully get some signal of tracking of ctDNA over time for each of the different disease types. Looking to see again as we do the dose modifications, what impact does that have on PK? And so being able to correlate that too of like what's the right dose in that way. And then the other big signal for me, frankly, is going to be the patient-reported outcomes. So it comes back to, is this something that's actually going to be tenable? And that's what's fascinating, particularly for a lot of these other diseases, but even for neuroblastoma, you have patients who've gone through 9+ months of really grueling chemo. And kind of they've bought into that, and they've said, okay, that's what my life's going to be, and this is miserable, and I'm puking my guts out, and I've lost all my hair, and either I'm gaining a ton of weight or I'm losing a ton of weight, and it's the chemo that they get for osteosarcoma, rhabdomyosarcoma, it's not pleasant chemo, but then when they enroll in the study, they want to get back to their lives. The big thing that I didn't emphasize here is, again, this is not immunosuppressive. So patients are able to get back to school, to their lives. They don't have to worry about their ANCs. They don't have to worry about repeat transfusions, things like that. There's still a lot they do have to care about. This chemo is not an easy drug. This is not where that's ending. The company is already on to their next generation drug in that way, and they're collaborating with COG still in that way. So that's where I think the patient-reported outcomes. Thomas Cash asked me the exact same question at ESCO of like, is this going to be signal changing? I'm like, I don't know. I think the signal that I want to see that's going to change is how do the patients actually see this, and is this going to be something that's tenable going forward? Because there's a range of maintenance approaches, right? And so go from DFMO and non-toxic in that way, but with kind of unclear what the efficacy signal is necessarily there either, particularly for patients who aren't in a state of a complete response. You can nuke them, but we need kind of more approaches that way. That's another thought that I was having yesterday of like, we use these metaphors of, we need more arrows in our quiver. We use lots of weapons. Patients come in, first we take out the Gatling gun and we just kind of like mow everything down. Then we nuke them, and then we start talking about arrows. And now we're talking about arrows earlier on and things like that. And like we need different types of weapons in this way. And this is what more I call a smoke screen. It's a smoke bomb. It's out there and it smothers the tumor in that way, but isn't necessarily as directly toxic, and at least that's the goal. So.
Anyone? One more question? Sure.
Hey, my name is Dave. In the context of this conference, so the family conference, this is an unfair question, so I'm prefacing with that. How would you, or anyone back at the science table, give advice for how we as parents can choose between these maintenance, right? This is exciting. There's DFMO, Iwilfin. There's the Sloan Kettering, the vaccine.
Yep.
And so I'm sure you're not going to stand up there and start saying yours is better than anyone else's. But like, how?
That's exactly what I was going to do, man. What are you talking about?
Yeah, exactly. Yeah. Have you seen my grant? Okay, well, go for it then. Like, how do we determine as parents which one to put our children on? So no pressure.
No. It's absolutely the right question, and it's the question we all dread as physicians. And I'm sure many of you have asked your physicians this: of if this were your child, what would you do? And we can never answer that. It's always a conversation that way. Here's what my perspective on that is. It's what your risk tolerance is. And I presented the data that we had determined at the start of the study I was going to be able to talk about at this point in time. Pre-planned evidence releases are the way to go. I don't think it's fair for studies to talk about patients, this patient or that patient, and this extraordinary outcome, things like that. No, that's putting your thumb on the scales. And so use the data that was kind of released and at least had some oversight. I didn't just get to put these slides together. There were 14 different people who I had to get permission from to be able to, and not permission as in like, oh, we don't want bad news getting out. No, it was, is this accurate data? Is this a fair representation of what the experience was? So you want to make sure that you're getting the right bill of goods in that way. Then I think it goes to, frankly, where you are in that journey. First relapse, single spot, resected or irradiated, got your consolidation, chemoimmunotherapy, patient's feeling good, less concern for kind of disease burden. Maybe your local doc is using some of these other tools that, frankly, we don't know what they mean yet. Like ctDNA, there is a ctDNA test available that's commercially available, but we don't know necessarily how to interpret that yet. And a lot of the big institutions have their own in-house versions of those things. Low disease burden, kid wants to get back to their life, things like that. Maybe you don't do maintenance, or maybe you do something that's a little bit later. Something like Cabo, it's an investment of not on the drug. The drug is free on the study, and it's an investment for the family to come to the center. It's an investment on the kid to suffer that risk of some of that side effect. So we had some kids who've done great, and it's really much more manageable in that way. But it's not an easy journey in that way. So I think it's always going to be individualized, and it's always going to be like, hey, where are you now? The family that I don't think they would mind me referencing them at least, but they got to me because they were 3 steps into that. They had relapsed, and we played whack-a-mole, and relapsed and whack-a-mole. Not we, their primary institution had, and they had tried some of these other approaches, and they said, okay, we heard about this Cabo thing. What do you think? Their primary doctor said, sounds reasonable. So they came to us, and that was my long-term survivor here with the neuroblastoma on the study itself. But that too was a decision, and I don't know if I would have recommended. Obviously, I would be happy to have the patient in first relapse come into the study too, because I think we get that experience too. But a very long-winded way to say it's a conversation, and take the kid's viewpoint into it, and hopefully you've developed that relationship with your physician, that they can fill in some of those gaps.
Okay, thanks.
Yeah.
Okay. Another question?
Hey, I'm Ashley.
Hi.
I just wanted to say thank you for your work, and just let everyone here know my daughter was on this trial, and she had 3 relapses that were getting closer and closer together. So we had tried the vaccine and DFMO. Not DFMO. DFMO wasn't available. DFMO was not available to us without chemo. And so anyways, we enrolled on this trial, very thankful. And so we're one of the patients in a long-term remission. If you want to talk to me or my husband, I'm Ashley, my husband's Josh. We're happy to talk about our experience on it. And also just, again, thank you for getting the word out. Our heart is that people would know about this, so we're really thankful that Dr. Shaw came and shared about it. So thanks.
Thank you guys for entrusting me. Thank you guys for telling Pat about me.
Anyone else have another question? No? Okay.
I'll be around, so feel free to come find me afterwards.
Yeah.
All right,
Thank you. We'll go ahead and take a break. Okay, we'll go ahead and there's some snacks again, eating again, for probably about 15 minutes or so. bright light. Oh, okay. We're going to go ahead and get started. Yeah, if anybody's in the hallway, come on in. Our next speaker is Dr. Daniel Morgenstern. He's a staff oncologist at Hospital for Sick Children in Toronto and associate professor at the University of Toronto. He originally trained and worked in the UK, primarily at Great Ormond Street Hospital in London, where he was clinical lead for neuroblastoma. He moved to Sick Kids Hospital in Toronto in 2016 as the director of their new agent and innovative therapy. And he's also the co-lead of the neuroblastoma service. He is also the medical director of the Oncology BMT Clinical Trials Support Unit, and since September of 25, head of clinical trials at the hospital. Dr. Morgenstern's clinical activities are focused on neuroblastoma and solid tumor patients participating in early phase clinical trials. His research interests are in the early phase trials, and in particular, the development of precision medicine approaches for pediatric solid tumors. Dr. Morgenstern.
Hopefully that'll balance. Thanks so much, Pat, for the introduction and for the warm welcome. It's a pleasure to be back here. Thanks, everyone, for listening. So this is, as you can tell from the title, quite a broad topic. I'm just going to start by giving my disclosures, as Pat has told us we need to. I don't think I'm going to say anything too controversial today based on those, but there they are. But this is what I'm planning to talk about. So Pat asked me to talk about sort of where we're at, recent developments, and really where we're going in the treatment for high-risk neuroblastoma. And so I've divided this up into treatment for upfront high-risk neuroblastoma, how are we treating newly diagnosed patients, what have we been doing, what are we doing next, where are we going, and then at the end I'll also talk about relapse disease and just give you a sense of the kind of overall perspective of how we're looking at that. And again, with this lens of where have we come from, what are we doing now, and crucially, where are we going to go in the future. Feel free to interrupt if there are questions as we go along, otherwise I'm very happy to answer them at the end. So let's start by talking about treatment for high-risk neuroblastoma from diagnosis onwards. And so the question really becomes, well, what is it that we need to fix about this? What is not good about our current treatment? And I think, you as parents who've gone through this will know very well, number one, the treatment really is unacceptably intensive and toxic. The treatment that we put children through with high-risk neuroblastoma is probably the most intensive and complicated treatment you could possibly imagine, because we're kind of now at the point of adding A and B and C, and then there's D, and what about E, and let's add some F in as well. And we know that is hugely toxic, both acutely and long-term. And of course, item number two is that treatment is ultimately ineffective for too many of our patients. We know that there are some patients where the disease does not respond well enough up front, something we call refractory disease. And of course, we're all worried about this issue of relapse, which is where the disease has responded well up front, but unfortunately disease comes back. And so clearly these two things, the toxicity and overall the lack of ultimate efficacy, are real challenges and things that we need to improve, and that's why we've still got a lot of work to do. This is the quick overview of current treatment for high-risk neuroblastoma, which has really just set the scene because all of the developments that we have going on are kind of based on this foundation. So I hope this is familiar to everyone, which is really this idea of induction chemotherapy at the beginning. In North America, we're now giving 5 cycles. This is surgery, high-dose chemotherapy, and we heard earlier on from Pat that we're now giving tandem, and there's clear benefit of tandem over single high-dose chemotherapy, radiotherapy, immunotherapy, and then potentially DFMO after the end of that. So this is the sort of shape of high-risk neuroblastoma that we've been using for a while. The most recent study that has finished, that we're still waiting to hear the answer from, is this study from COG called 1531, which was to say, could we add something to this chemotherapy backbone to try and improve the response rate? And the thing that was then added to it was the MIBG therapy, which we'll hear a bit more about later on, but essentially this is a way of using the MIBG that we normally use for imaging, putting a much stronger radioactive tag on it, and then using it for treatment. So this was a randomized study. Some patients got the chemo alone, some patients got the chemo and the MIBG, and we're really all waiting probably till the end of this year to know what the answer for this study is. Does the addition of MIBG therapy to induction improve outcomes or not. It's sort of adding an F and a G and an H onto the treatment. So I think many of us have got kind of mixed views about this. Obviously, it would be fantastic if we improve outcomes, but if we do improve outcomes, are we now adding yet more complexity and yet more things to our treatments? The other thing is adding lorlatinib. So ALK is one of the rare mutations in neuroblastoma where it's a common recurrent mutation in neuroblastoma, and crucially, we've actually got very good drugs that inhibit that pathway. And so for a while, COG, and Europe is just kind of getting on board with this as well, has been asking the question, if we can identify those patients with a specific mutation at diagnosis, a mutation in ALK, can we then add an ALK inhibitor drug sort of all the way through treatment and into maintenance to improve the outcome for those patients? That study is ongoing at the moment. We don't yet know the answer to that. And then there's the study that we're doing at the moment. And so you can see that, again, this is taking the same backbone of chemotherapy, same 5 cycles, and is adding onto it, in green down here, dinutuximab. So this is taking the idea that anti-GD2 antibody, which we've routinely used at the end of treatment, is a good thing. We've then become very excited, as I'll talk more about in a minute, about the use of chemoimmunotherapy in the relapse setting, because it seems that they work very well together. And now what we've done is take the leap of saying, well, if chemo together with immunotherapy is good in the relapse setting, what about doing that right from the very beginning? And this was work that was initially led out of St. Jude, who ran a study that was very successful in terms of outcomes at one institution. And COG is now therefore testing this in a randomized study, which is ongoing at the moment, to say, can we further improve the efficacy of the initial chemo if we give antibody together alongside that? And then we're still giving antibody again at the end. So this study is ongoing now. Of course, we don't know the answer to that and won't do for quite a few years. And so then I just want to talk about, well, what might be coming next in the short term and where are we going in the long term? So one area that there's a lot of discussion about at the moment is tandem high-dose chemotherapy. We know from that previous study that was done by COG that tandem has superior outcomes than single, which is, again, great because we've improved outcomes, but also a bit disappointing, frankly, because it means that we're now stuck with more and more intensive treatment, and we know that that comes with acute and significant long-term toxicities. And there's been a lot of discussion, pushed actually mainly by patient advocate groups initially, and now really taken on by the scientific community to say, can we do anything about this? Do we know that we really, really, really need that high-dose chemotherapy, especially if we've got more effective treatments like anti-GD2 and chemoimmunotherapy? And so there's a lot of debate at the moment about how to actually turn this into a trial, but there are thoughts about, could we do a study where we swapped out that tandem high-dose chemotherapy and instead gave chemoimmunotherapy at that point? It's a complicated study to think about because whilst we're really keen to reduce the toxicity of our treatment, we're also very anxious about not doing something that actually leads to worse outcomes. And so it's a really tricky balance about designing that. But that is definitely under a lot of active discussion at the moment about how we might think about testing that. One of the other things that is also under discussion at the moment is, although the treatment in US and Canada, I've got to say, and Canada every time because that's where I'm from, and Europe is broadly the same in that the pattern is the same because we've got induction chemotherapy, consolidation, maintenance. The details of the individual components of this are different, and I've not put details of all the drugs down here, but the chemotherapy that routinely is used in Europe is quite different in terms of how it's given than in North America. They give chemotherapy every 10 days on a kind of continuous rolling schedule, very intensive. And so that makes studying neuroblastoma a bit complicated because Europe is doing one thing, North America is doing another thing, and it makes it slightly challenging to add new drugs and to test things together. So one of the things we're working on at the moment is, might it be possible to get to a common transatlantic induction backbone where both sides of the Atlantic do the same thing in terms of chemotherapy, which then means that we could add things to that chemotherapy, and if it worked in US, we would automatically know that it would work in Europe, whereas at the moment we have to do the study again because of the different chemotherapies. So that's something that's being worked on at the moment. And then I just want to be a bit more speculative and say, well, if we look 10 years into the future, where might we be going with the treatment of high-risk neuroblastoma? So, we already do a lot of this tumor sequencing, and Meredith Irwin will talk more about that, I'm sure, shortly, to look at the real detailed genetic characteristics of the individual tumor at the beginning. But to be honest, at the moment, we don't actually do that much with that information because we're not well able to use that information to actually make treatment decisions. So one thing we do at the moment is if we identify an ALK mutation, then we might add an ALK inhibitor throughout that patient's treatment. But I think as we get cleverer about this and learn more about neuroblastoma, it may be that we're able to break out other subgroups of neuroblastoma. And you heard Pat Reynolds talk this morning about telomerase and ATRX and ALT. And it may well be that that is another group of neuroblastoma where we're able to say, actually, you know what? We know that you're not going to respond well to our standard treatment, and we're going to give a different treatment specifically for that genetic subtype. We're not there at the moment, but that, I think, is the direction. And then, the other things are that we may be able to add extra to the induction chemotherapy, maybe anti-GD2, which I've already talked about, and then this other thing that I'll mention later, again, called antibody-drug conjugates, which are a new type of medicine that may well come through in the future. And then what about other things that we could think about are, at the moment, we routinely give 5 cycles of chemotherapy to everyone. We test disease status at the beginning, and we test disease status after those 5 cycles. But another thing that's being thought about at the moment is maybe to do a response assessment earlier. And if the disease has shown an excellent response early on, maybe we could give less chemotherapy and move ahead with the next parts of treatment. And if the disease response is not quite as good, carry on with more chemotherapy. And then on the consolidation front, radiotherapy, I think, is going to be there for a while. But CAR T-cell therapy, at the moment, we're really at the very beginnings of learning about CAR T-cell therapy. But maybe if we can get it up and running and it works, maybe it will become a routine part of treatment for high-risk neuroblastoma. Instead of giving high-dose chemotherapy, maybe we'll give CAR T-cell therapy to every patient, and that maybe will help to maintain a remission. And then in the maintenance setting, at the moment, we're very used to giving anti-GD2 antibody together with GM-CSF. Maybe there will be other drugs that we can add to that to enhance how that anti-GD2 works, and I'll talk about some of that in a minute. Maybe there will be vaccine strategies that are successful and able to broaden out. Maybe there'll be other maintenance strategies to make sure that we're trying to keep patients in remission. And I think the other thing is about molecular testing and ctDNA and other ways of really looking at, have we, at the end of treatment, really, really, really got rid of the neuroblastoma? Because we know that our scans are only as good as, 90%, 95%. We know that you can definitely have disease hidden away that we can't see on a scan, but that can be lurking there. And at the moment, we don't have a way to pick that up and to do something about it. So this is sort of speculative for the future, but it may well be that we then adapt maintenance treatment, that we adapt the total amount of treatment depending on the individual patient's disease. So that is sort of a whistle-stop through treatment for high-risk neuroblastoma from the upfront perspective, where we've come from, what's being tested now, and where we're going. And then I just want to talk about treatment for relapse high-risk neuroblastoma, because actually a lot of what we're thinking about and developing in the relapse setting is what we're hoping ultimately we will then be able to move forward into the upfront setting. It's that we need to start by testing it in the relapse setting before we bring it forward. So just a kind of few introductory words about relapse. So treating relapse disease is really challenging. And one of the things is because when we have a patient with newly diagnosed high-risk neuroblastoma, we have a pretty fixed menu in that there's not really a lot of choice about what to do. We know, or we think we know, what the current best available treatment is. It's to give some A, and then to give some B, and then to give some C, and then to give some D. And so the conversations with you as parents are, we've kind of got to suck this up, this is what we've got to do. In the relapse setting, it's much more complicated because we kind of have a wide-ranging menu of options. It's you can pick this, or you could pick this. If you pick this, then you might want to follow it up with this, but you might also want to follow it up with that, or we could start with this. And so the decision-making is a lot more complicated because it's not just a question of us saying, is A better than B? It's also, where are we really going with this? What are we trying to achieve? How many cycles of this are we going to do? Where are we going to end? And the other challenge in the relapse setting is that often we as clinicians are dealing with imperfect information to be able to guide you and to guide ourselves about what treatments to use, which is that most of the studies that we have in the relapse setting are single arm, so they're not randomized. They're one group of patients treated with a new drug, phase 2, so that means that we kind of know what the dose is, but we're testing the efficacy. But generally, when we say that the drug works in the relapse setting, what do we mean by that? Most of the time, what we mean is a scan got better, that the MIBG scan had 20 spots, and now it's got 2 spots. From our perspective as oncologists, that's a fantastic success. That's 20 down to 2. That's an objective response. The drug worked. But what really matters is, does that actually translate into longer survival, better quality of life? Does it mean that there's a chance of cure? And those are questions that are often not asked in the study because those are answers that take a lot longer to come to. So it's very challenging, I think very important when thinking about relapse treatment to bear in mind when we say something is working, what we mean by that may not be what you mean by it or what all of us want to mean by that, which is really about long-term outcomes. We're often stuck talking about tumor response. And then the other challenge, of course, is where do we fit each individual treatment in that overall strategy for managing relapse? And we heard a bit about that earlier on just now with the cabozantinib study, which was to say, if you've had treatment A, what might come after that? Something less toxic, maybe, something that's in some sort of maintenance. And again, fitting all of that together is still very complicated. And then this slide is just to sort of say there's also this balance that has to be struck in treating relapse, I think, between treatment intensity versus quality of life, because often in the relapse setting, we are not able to say a cure is available here. Often we are saying we have treatments that are available that can control the disease, sometimes control the disease for many years at a time. But if we're not ultimately able to get to a cure, we really have to be careful about the intensity of the treatment and the impact of the quality of life, because if we are extending life, but with all of that time in hospital, there's a question as to what we've really achieved there. And so there's a lot of controversy still because we just don't know the answer as to whether it's best to treat relapse very intensively early on to try and get the maximum depth of disease control as quickly as possible, or whether actually adjusting the treatment based on the patient's symptoms and maybe going more gently at the beginning if the patient is well is the right direction. I don't think any of us know the answer to that. There is some good news in the relapse setting. So the kind of takeaway message from this graph. So this is data from what's called the INRG, which is a database of patients from across the world with neuroblastoma. And within this, we looked at outcomes for patients after relapse. So these are patients with high-risk neuroblastoma and their survival after relapse. And the kind of important curve is the one in blue, which is really to show that over time from kind of the mid-90s to the mid-2015s or so, we have made significant progress in survival after relapse. The follow-up is still quite short, it's only 2 years, but you can see a significant change from 16% to 32%, which means that all of the new treatments that we have do seem to be moving the bar and that we are able to begin to improve outcomes for relapse patients, even though there's clearly still a lot to be done. So then I just want to turn now and give some thoughts about what are the types of things that we're using in relapse, what's coming down the line, where are we going to next? And so I've just kind of broken this up in terms of how to think about different treatments in relapse, because there's kind of so much going on in neuroblastoma, it's kind of hard to keep it straight in your head. So this is kind of in the context of what's new and emerging in the relapse setting. So number one is chemotherapy, and the answer is there's not actually that much excitement in the field about chemotherapy at the moment. I think most of us feel we've probably got most of the cytotoxic chemotherapy agents that we're ever going to have. Many of these patients are very heavily pretreated. The thought of giving more toxic chemotherapy with more nausea, vomiting, myelosuppression, hair loss, all the rest of it is not attractive. And so often chemotherapy is an important part of the backbone, but I guess simplistically it's not where the cutting edge of science is at the moment in the relapse setting. Immunotherapy, there's a lot of interest in in neuroblastoma especially. And I think neuroblastoma is, an outlier in solid tumors where we have proven that immunotherapy works. So the use of anti-GD2 in upfront treatment for neuroblastoma is based on a randomized study demonstrating the benefit of that in improving outcomes. And it's one of the rare situations in solid tumors where we actually know that the tumor can respond to an immune type of treatment. And clearly there are lots of different ways of using the immune system to treat a tumor. As I've mentioned already, we think in the relapse setting, if you get the anti-GD2 and add some chemotherapy together, that helps to make it more effective. And so we're looking at, can we then add something else on top of that to make it even more effective? And that's one big growth area. Antibody drug conjugates I'll mention again in a minute. And then there's a whole nother way of using the immune system, which is about cellular therapy, which I think we're going to hear about in a minute, the whole story of CAR T cells, NK cells, and so on. So that's immunotherapy. And then there's a whole other category called molecular radiotherapy, which I've mentioned already in passing, which was the MIBG therapy. This is where you're kind of trying to take medicines and inject them into the patient, and those medicines go to particular targets and take radiation to those targets and kill the cancer cells as a medicine using radiotherapy. And then the fourth category is where we're really hoping the future is going to take us, which is this kind of idea of precision medicine. You find a specific target, you have a drug that exactly hits that target, and you take out those cancer cells with minimal toxicity to the rest of the patient. That's the kind of idea for the future. So let's just kind of talk briefly about those. So chemotherapy, just to be very brief background about it, it's now what we kind of know and love for treatment of neuroblastoma that has not behaved itself. And this comes from the previous COG study 1221, and also a similar study that was then done in Europe with the European antibody called dinutuximab beta, which is similar but slightly different. The takeaway message from both of these studies is that it really looks like if you add antibody to chemotherapy, it's much more effective than the chemotherapy alone. And so we've really then adopted that as our standard treatment for relapse disease. The most recent study that was done was to take that backbone of chemoimmunotherapy, temozolomide, irinotecan, dinutuximab, GM-CSF, and add onto it this drug called DFMO, which I suspect many in the room are familiar with. This is the pathway of these lovely compounds called putrescine, spermidine, and spermine, which are polyamines that none of us had ever really heard much about until DFMO came on the scene a few years ago and we had to learn about. But essentially, these are molecules that have multiple roles in cells in terms of proliferation, survival, migration, all of those kind of cancer things. And there's this particular enzyme called ODC1, for various reasons to be excited about that in neuroblastoma, and DFMO blocks that enzyme. So the idea was that we could add this drug at a pretty high dose to chemoimmunotherapy with the aim of improving outcomes. Unfortunately, that study did not show a benefit of adding DFMO. So you can see the overall response rates here between the control arm, arm A, and the arm B, which was the DFMO, and you can see the response rates pretty much the same, actually maybe slightly numerically lower with the DFMO. So really, unfortunately, in that context, no evidence that DFMO was able to improve the response to the chemoimmunotherapy. So that was the study that's kind of been finished. And then there's lots of other studies ongoing. So in Europe, they have a study now called Beacon-2, where they are adding this drug called bevacizumab, which is a VEGF, so that's a vascular endothelial growth factor. That's an antibody that blocks the production of new blood vessels. And they showed previously that that was effective if you added it to the chemotherapy. And now they're adding that together with the anti-GD2 that they have in Europe. And there are multiple other arms that they're working on at the moment. And then this slide, which I tried to put pretty colors on to make it look more attractive and less threatening, is really just to kind of give you a sense of the overview of all of the other things that we're thinking about adding onto chemoimmunotherapy. And this is really where there's a lot of interest and excitement in the field at the moment, is to say chemoimmunotherapy is great, but what else can we add on to that to try and make it better? So very briefly, and Araz will talk about some of these in more detail later in the day, immune checkpoint inhibitors, there's a study that we're just working on at the moment to get this going through the NANT consortium. This category of immune modulators, things that change the immune system called cell mods. There's a study just opening now through the COG. Other things that we can do to ramp up the immune system. Cytokines are drugs that modulate, that stimulate the immune system. There's one called IL-15, which is being tested now in a study that's open in NANT. Could we add extra immune cells on top of the chemoimmunotherapy to make it better? Yes, we can. There's a study with NK cells at the moment. So these are the things that are happening. And then down here, there's a whole bunch of other stuff which is just on the cusp of happening, where there's some preclinical data and we're waiting to translate it into the patients. Other checkpoints like macrophage checkpoints, copper chelation, so that's kind of binding copper in the tumor microenvironment to change how the immune cells function. And there's also some preclinical data on ketogenic diet that might enhance the efficacy of the immune system's response to chemotherapy. So this is really a big, big growth area, all of these different treatment combinations, and lots of things to be tested in the future. So I've mentioned antibody-drug conjugates several times, but I haven't really explained what they are. But this is, in a way, one of the next big categories of medicine that is all the rage now in adult oncology and hasn't yet really made it much into pediatrics. And we're just at the beginning of testing these in the pediatric population. The idea essentially is that you can use an antibody, and we already do this with the anti-GD2, to recognize specific cells, specific markers in the body. And so the anti-GD2 that we use at the moment is an antibody. We call it a naked antibody because it's literally just an antibody that binds to GD2 on the cancer cells. And we then rely on the body's immune system to actually do something, to recognize the antibody and then to kill the cancer cell. With an antibody-drug conjugate, what you do is you take that antibody and you use the antibody to bind onto a marker on the cancer cell, but you then add something onto the antibody, and that's this bit down here at the bottom with a linker, and then this red bit here, which essentially is a cytotoxic drug, something really dangerous and poisonous. And when this antibody binds to the cancer cell, to its target, it gets taken up into the cancer cell, the antibody gets broken down, the drug gets released inside the cell, and then the idea is that it kills that cancer cell. So it's really a way of using very toxic chemotherapies, but to target them towards specific cancer cells. Excuse me. And there's lots of different targets that we can use. GD2, of course, is one that we're most familiar with in neuroblastoma. There's also something else called B7H3, and there's this other one called ROR1, and I've just put that because these are all antibody-drug conjugates that are being tested now for the first time in children. We're just at the beginning of this, but it's possible that in 5 to 10 years' time, these become the class of drugs that we're even using in the upfront setting as a way of really honing in on the neuroblastoma. And then I'll just mention that ALK, that we've talked about in terms of a mutation, is also expressed in most neuroblastoma cells on the surface, and so that's also a potential target for an antibody-drug conjugate, and the team at CHOP are in the process of developing one of those now. So that's a whistle-stop on antibody-drug conjugates. And then molecular radiotherapy, just to kind of come back to this, there's a lot more, I think, that's going to come down the line for this in pediatric oncology. Again, this is something that is very much the rage in adult oncology, especially prostate, is saying, let's take a radioactive compound and then let's target it to specific cancer cells by adding it, by linking it to a specific target molecule. So this is what we already do for MIBG therapy. We have the MIBG, which is this, which is taken up by neuroblastoma cells because they have the receptor for the MIBG, and then we bind it to a radioactive compound, which is 131 iodine. And there's lots of new ways of doing this with different types of radioactive compounds here and different types of targeting here. And again, Araz will talk about a new study that we're just planning through the NANT consortium for that as well. And then in the closing stretch, I just want to highlight a few molecular targets. And there are many, many, many of these that are going to be relevant in neuroblastoma. And I've just selected 4 to kind of give you a selection of what I think are the most interesting of them. So ALK, we all sort of know and love because, as I said, it's become the poster child for precision medicine in neuroblastoma because it's one of those rare circumstances where there's a gene and we've got a drug that actually impacts that abnormal gene. We've got very good small molecule inhibitors, and now what we're beginning to do is to shift towards saying, well, sometimes the tumors develop a resistance to that. What could we do to overcome that? Maybe we can give an ALK inhibitor plus something else, an ALK inhibitor plus this or plus this, and there's lots of work going on as to what those combinations will be. The other molecular targets are this thing called the RAS pathway. RAS-MAP kinase is a key signaling pathway in many, many cancer cells, and it's not normally that relevant in neuroblastoma at the beginning, but we're increasingly seeing these mutations when we sequence neuroblastoma at relapse. And the bottom line is we're kind of waiting for drugs that are going to target this pathway. Those of you who watch the news may remember at the ASCO meeting this year, one talk got a standing ovation because of a breakthrough of this new RAS inhibitor for pancreatic cancer. And so there's plans for that to be tested in childhood cancer and a study coming through COG later this year. So we're kind of waiting to see whether we can get good drugs to inhibit that pathway. You've already heard this morning about ATRX, ALT, telomere maintenance, and I think it's very clear from Pat's work and others that this is a really important pathway in neuroblastoma and may well be correlated with failure to respond to our current chemotherapies. The problem is we don't actually have very good drugs for this at the moment. So we're kind of waiting for the drugs to come, but this, I think, is going to be a really important group of molecular targets down the line. And then finally, just on the DFMO front, I've already shown you this figure, and I've just added a little bit here to the left-hand side, is to say, maybe, the DFMO inhibits how these things are made from ornithine by blocking this enzyme. But ornithine also relies on other parts of a pathway to have enough of this. And so it may be that there are ways of inhibiting this pathway more strongly by hitting it not just at one point, but at other points as well, by either inhibiting, depleting the things you need in order to make the ornithine in order to make these. And so there's a lot of preclinical work going on and potentially some interesting clinical trials to come down the line. So those are just kind of 4 snapshots of molecular targets. There are many, many others. So in conclusion, I think, immune therapy we are very excited about in neuroblastoma. This whole idea of chemoimmunotherapy plus something, I think, is definitely something we're really testing. We do want to try and move towards personalizing therapy based on characterizing the tumor. We're already doing a lot of the characterizing, and Meredith will talk about that. We're not very good at the personalizing at the moment, and we've got to get better at how to actually use those data to make different decisions for different patients. We clearly need to improve the effectiveness of current treatments, and ultimately our hope is that maybe with these new treatments, rather than adding and adding and adding and adding, maybe we'll eventually get to the point where we can begin to take away some of the most toxic parts of our current treatments because we've got better, more effective treatments with less toxicity. That's ultimately where we need to get to. And I'll just finish by acknowledging everyone in the community, all the patients and families, and these collaborative groups, and happy to answer any questions. Thanks.
Thank you. Does anyone have any questions? We have one, two. Go ahead.
Hi, my name is Janelyn.
Hi.
I'm not sure you want to know that, but
I'm very happy to know that.
the last presenter did. So. Okay, so this maybe, again, is another unfair question, but our son has relapsed multiple times, and we've been on this journey for 7 years, and we have done mostly anti-GD2, so chemoimmunotherapy, and recently I've started wondering a little bit, should we have varied that along the way? And so my question is kind of that, like, I kind of started wondering, why didn't our team come to us and say, hey, while we're doing this immunotherapy that seems to be working well for you, do we want to look at something where we add another agent into it, like the NK cells or the IL-15s, and get you on trial for that? Or maybe we should throw in some MIBG therapy. I'm just kind of wondering now, should we have varied that a little bit more? You talk about personalized care, but you're also excited about the chemoimmunotherapy. So I'm not wording this very well, but is there a value to as you're going through, a family is going through relapse, varying the types of ways that you hit that?
Yeah, I think the easy answer is we don't know. I mean, the problem I think is that presumably the treatment that your son got was working at the time, which is why they carried it on. And what we really don't know is if a treatment is working, is it worth trying to swap out to try and make it work better.
That's why it's not a very fair question for me to ask.
Exactly,
I
because
get that.
but it's
Yeah.
really important, because the problem is there's always the worry that it might work less well.
Yeah.
And this kind of reflects us not having a good enough understanding at the moment about what really matters in terms of long-term outcomes. Because on the one hand, you could say, well, if treatment A is working, but it's only working 90%, if we could find a treatment that worked 99%, that would be better. But on the other hand, we don't actually know that that really changes long-term outcome. And so I have this anxiety as well with patients that we treat is, the classic example is when you've got stable disease in the relapse setting is this good enough? On the one hand, great, we've got disease control, but on the other hand, we're not actually making this disappear. Is this good enough? Well, I could change to something else, which hopefully would be better, but it actually could be worse, and we could lose control. And so I think it's really hard in terms of decision-making for an individual patient because we never have a way of knowing. And I think this is also the challenge that we have in the relapse setting, which is that even if we had proof in a study that we did chemoimmunotherapy versus chemoimmunotherapy plus X, and we showed that the adding X was proven to be better, that still doesn't actually mean that it's going to be better in an individual patient, because all of that is averages. And so it gets really challenging about how to make the decision for the individual patient. And I think the final thing I'd say is, I do worry about us using chemoimmuno, because it's like giving anti-GD2 with everything. It's kind of becoming the ketchup of neuroblastoma, which is just stick it on everything. And I do worry that we may end up with resistance or loss of GD2 expression. And that's why I think we've got to find these other targets, be those immunotherapy targets or other small molecules.
Thank you.
Okay, another question?
Yeah, I was wondering if you could expand more on the ketogenic side. Aside from our traditional teams, we have also sought a functional oncologist. And one thing that our daughter did outside of traditional genetic testing was like a cheek swab type. And so it's a curious area for me because her results showed like pathways where a lower glycemic insulin stabilizing approach was beneficial for her. This is after treatment, so the body's changed, but just curious if you could give more insight.
Yeah, I mean, a little bit. I have to confess, I'm not an expert in this area. I think it's really challenging to make it practical. I mean, the bit I worry about from a clinician is many of our patients are already going through so much difficulty from a nutrition perspective, keeping their weight on, coping with chemotherapy. Mm-hmm. I worry about dietary modification making life even more difficult for children and their 100%. Families. And so to me, it feels like we really need, there's a bit of a burden of proof to say that it's worth doing it. I think, I didn't have time to show it, but there are some interesting preclinical data in the lab now from mice suggesting that if you have them on a ketogenic diet or you add ketones, that does change their response to chemoimmunotherapy. I think, to me, simplistically, it makes sense to imagine that metabolism is going to be important in cancer survival, but I kind of feel it's a complicated and not entirely benign intervention, and so I feel cautious about recommending it without there really being robust evidence. So I guess what I'm saying is ultimately we'll need to get to a point of a trial to say, does it really help? Mm-hmm. And then I think the question is going to be, is the trial actually of a ketogenic diet, which is really tricky to implement, or can we kind of extract what is the element of the ketogenic diet that's really important and maybe turn that into a medicine and test that, because 100%. That will be a bit easier in practice.
Yeah, especially like my daughter was 3 at the time, like we can't really force you or, it's a toddler, basically a preschooler. A lot of these kids are not already going to be up for changes even more. But I was just curious, because it's an area that nutrition is like a small window that we talk about, but just super fascinating. So thank you.
Thanks. Go ahead, Josh.
I was going to ask about your perspective on liquid biopsies, what the role is, what you see the future being. Is there it becoming like a standard thing in the future? Any perspective there? Good question.
So I think that I see 2 roles for them. So I think one role, and we're doing this at Sick Kids and many other places are doing this already, is We know that the genetic profile of neuroblastomas changes over time, and so especially at relapse, there can be a whole bunch of different mutations that were not present at diagnosis, and that is probably the case for relapse 2 and relapse 3 as well. And sometimes those molecular changes can suggest treatment options like ALK inhibitors. And so I think ctDNA is really useful for looking at mutations in the tumor if you can't biopsy the tumor, and often you can't at relapse because it's in bone and difficult to get at. So that's kind of use case one that is up and running. I think the really interesting second use case, which I just kind of mentioned at the end, was can we get to a ctDNA test that really tells us about minimal residual disease, that idea of detecting really tiny amounts of neuroblastoma that are lower than the level that we could detect on a scan. Because you could argue that if at the end of upfront treatment we could separate out patients with absolutely no neuroblastoma at all from those patients who look like they have no neuroblastoma but actually do have detectable neuroblastoma in their blood, that maybe we could do something about it at that point before there was frank relapse. And the challenge is the technology is quite complicated to do that reliably because neuroblastoma doesn't have many recurrent mutations, and so it's complicated to find an assay that will reliably pick up neuroblastoma at very, very small levels. But those are the two areas, I think, for the future.
Thank you.
One more question?
Can you spend a few minutes or seconds talking about why we should be excited about these new ADC trials? I mean, I've heard a lot about them. Like, for example, the B7H3, my understanding is they've tried to target this multiple times before in different contexts with different therapy and have failed. And so why should ADC be different? Is there a reason, or is it just a hopeful thing?
Sorry, the failure you mean of what, of the B7H3 antibody?
No. Okay, obviously I don't know the details. Dr. Modak yesterday was talking about how they've targeted this in different ways previously and nothing has taken. So right. I don't know the details of that.
Okay, yeah. I mean, I think the bottom line is we don't know really anything about how effective these drugs are going to be in neuroblastoma because the studies in patients are just getting started now, and we're at the point of doing the phase 1 studies of working out what the dose is. I think the excitement comes because in adult oncology, these are one of the major breakthroughs and are increasingly the way of delivering more targeted therapies. And they're kind of a way of delivering a targeted therapy, but without needing to have a specific mutation to target, because what you're targeting is sort of the physical tumor cell and getting the drug to the tumor rather than a specific pathway within the tumor. So I think our excitement about them is that they've been very successful in multiple adult diseases. It maybe gives us a way of targeting neuroblastoma, not just with GD2, but also with maybe ALK, maybe with B7H3, maybe with this, maybe with that, maybe the other, and doing something which is different from what we've been doing at the moment in terms of cytotoxic chemotherapy or naked antibody. I mean, I think they've absolutely got to prove themselves, but I flag them because I think we're all excited about them as a new class of agent. We just don't have the data at the moment to say that's really going to help.
All right. Thank you. Okay. Thank you, Dr. Morgenstern.
Thank you.
Our next speaker is Nico Dalton. He obtained his PhD in biochemistry from the University of Buenos Aires in Argentina. During his PhD training, he studied the effect of metabolic syndrome in prostate cancer metastases. Now as a postdoc in Dr. Robbie Meisner's lab, where they are aiming to develop new and effective immunotherapy approaches for cancer. Nico is interested in understanding ganglioside biology in pediatric malignancies in order to discover new vulnerabilities and targets for immunotherapy. His talk today is on CAR T-cell and monoclonal antibodies for the treatment of high-risk neuroblastoma. And believe it or not, he does have a life outside of medicine, and he does like to go on hikes, hit the gym, and hang with friends. Nico.
Thank you so much for having me here. I thought I was going to have to introduce myself, so thank you, Pat. What I realized here in all the previous talk is what a lot of the things that I'm going to show you are going to be a bit redundant. and I think I'm late for the party, but if I, at any point, I'm explaining something too much, you can stop me and tell me to move on. And also I have an accent, so my English is not going to be as exquisite as the previous presenter, but bear with me. So I have no disclosures because I'm just a PhD. And the first thing I want to show is this graph, which kind of has something to do with what was previously stated. And what this graph is showing is the frequency of somatic mutations in tumors compared to the normal tissue. So if something is to the right of this graph, means that it mutates a lot, so that the DNA of the tumor cell will be very different from the DNA of the normal tissue. Well, if it is on the left side of the graph, it means that the DNA of the tumor cell is not so different from the DNA of the normal tissue. And most pediatric cancers land right on the left side. And what I mean with this is that a tumor cell won't be necessarily too different from a normal cell, and that makes it more complicated to the immune system to detect that as a threat and eliminate it. And that is because of the way the immune system works. And I told ChatGPT that I was going to present some immunology stuff to people that are not necessarily scientists, and that's what it came up with. And I just heard that Aras is doing something similar, so I am not too ashamed of this. So very briefly, the way the immune system works is very good at detecting non-self. So our immune system is very good at finding out things that are not part of our body. And if you can imagine, if you have a viral infection, then you have a virus that is inside of one of your cells, making more viral proteins that are very different from the cells of your body. So we have these specialized cells that are all the time probing and looking around for things that are off place. And when it finds these cells, it alerts other immune cells that then activate and coordinate an attack on those cells. And hopefully they remove the threat, they eliminate the infection. For cancer, the principle is the same. But if, as I showed in the previous slide, if the tumor cell is very similar to the normal cell, then most times the immune system won't detect that as a threat until it's too late. So what we need to do, and what immunotherapy tries to do, is to re-educate the immune system, point it in the right direction, so they can detect the tumor cells and eliminate them. And we talked previously about dinutuximab, or yesterday they mentioned naxitamab, which is another anti-GD2 monoclonal antibody. GD2 is this molecule, which I'm going to talk more about later. And what is undeniable is that anti-GD2 immunotherapy has been a tremendous help in remission for neuroblastoma patients. And another thing, because somebody just asked about ADCs in neuroblastoma, anti-GD2 therapy only works in neuroblastoma. And it wasn't intended to be for neuroblastoma. It originally was a small cell lung cancer trial. So we actually don't know what is going to work best for a certain disease. So, and here is the part where I might get a bit redundant. We've been talking about monoclonal antibodies a lot, but what are those? And to talk about antibodies, first we need to talk about antigens. An antigen is anything that the immune system will detect as a threat and mount a response against. But what's interesting about antigens is the epitopes. The epitopes are the different parts of the antigen that the immune system actually recognizes. And normally in our bodies, we have what is called a polyclonal reaction. So one single antigen, let's say a protein, will be detected by many different immune cells, many different T cells and B cells, and they will mount responses individually. Each cell that recognizes an epitope is called a clone. Since we have many cells detecting the same antigen, we have a polyclonal reaction. So as an example here, we have a ton of antibodies. But these antibodies are going to have different specificities, different activities, different affinities. So what we do in the lab is we take one of these B cells, for example, that are making an antibody of interest, we fuse it with a tumor cell, we make an immortal antibody-producing cell, and that antibody-producing cell will make only one type of antibody. All the antibodies are the same, they have the same specificity, affinity, etc., and that is what we call a monoclonal antibody. And while it's very nice to draw antibodies with a Y, they're actually way more complicated. Don't worry, we're not going to go into all of this. The only important thing is that the antibodies have two main regions. One is the Fab, or FAB, which is the part of the antibody that binds to the antigen. And then we have the FC, which is the part of the antibody that will interact with the immune system, with macrophages, with NK cells, etc. And also, since I'm a wet lab person, I wanted to point out that we use monoclonal antibodies all the time for detecting proteins, for microscopy, for flow cytometry to know what's on the surface on the cell, and or ELISAs. And I'm sure you all have done an ELISA sometime in your life because it was on pregnancy tests. So one of the applications, and I did this before I knew you were going to hear and see a lot of flow cytometry plots, so I apologize. But the way we do is we take a tissue, we digest it so it's single cells, then we incubate with antibodies that target the things we want to discover, and these antibodies have a color so we can see them. Then we put it in a machine. This is our flow cytometry at the lab. I spent many, many hours here. And for me, this is great because what a flow cytometry does is this machine makes the cell go one at a time, and then it gets interrogated by a laser, and that laser will give us a lot of information about the complexity of the cell, the size of the cell, and also, depending on the antibodies that we use, what's on the surface of that cell. And then we can analyze that data, and we'll have these nice plots, which on one axis we have GFP, which is the green fluorescent protein, and the other one we have APC for gangliosides, for example. But we can also show it like this, and it's the exact same data. We're only looking at one variable, or we can look at it like this, and again, the same data, we're just looking at one variable. But what's important, or what you probably care most about, is the therapeutic applications of monoclonal antibodies, and today we're going to talk about two. One is naked antibodies, like dinutuximab, and the other one is CAR T cells, which is T cell therapy, which is, I think, almost science fiction. It's super cool. So again, some biology. Gangliosides are synthesized in a very complex pathway. I don't even understand it, so I make it simpler. And this is the simplified ganglioside pathway. So in order to get GD2, and this is going to be more relevant later, we need these three enzymes. And what's important here is that GM3, which is there in the middle, is the substrate for ST8SI1 that will make GD3. And then GD3 will be converted into GD2 by the enzyme B4-ganon1. But GM3 is also substrate for that enzyme to make directly GM2. So a few years back in the lab, we had this model of neuroblastoma. We injected it into the mice. We treated with dinutuximab in red. It works at the beginning, then all the mice relapse. And when we look at the tumors after relapse, in black you can see is the amount of GD2 that a tumor that wasn't treated has. But a tumor that saw GD2 saw anti-GD2 lost GD2 in the surface. So we had this hypothesis. First this question, why is losing GD2? So normally, if we look at cells, we have high levels of GD2 in neuroblastoma, but low level tumors that were treated with anti-GD2. We saw that this enzyme right there was downregulated. So the tumors were losing one of the enzymes needed to synthesize GD2. If we lose this enzyme, we're essentially losing the right side of the pathway. So we don't have GD3, so we cannot have GD2. But this other enzyme is still there, is still in the cell. So all the GM3 that now is accumulated is being turned into GM2, which would be this analogy. So we need to prove it that. We did a different experiment in which we treated the mice with two different anti-GD2 therapies, CAR T cells or monoclonal antibodies. And when we look at the tumors in blue or in red, they have completely lost GD2. And when we look at GM2, it was elevated. So we got very excited and we said, okay, can we show this, like, is this translatable to patients? What's going on there? So in collaboration with NANT, we had bone marrow samples from patients that have been treated with chemoimmunotherapy and then relapsed. And in here we have GD2. Most of them still retain GD2. One patient had very low GD2. But when we look at GM2 in all these patients, all of them have it. Patient 4 was interesting because we could also get pre-chemoimmunotherapy samples, and before the treatment, GD2 was there, and it was lost after. So now the second idea or question is, can we target GM2? Like, it's fine, it's there, but what can we do about it? So again, some biology. The way the antibodies communicate with the immune system or help eliminate tumor cells is through many processes. One of them is called antibody-dependent cell phagocytosis, in which the macrophages, which are cells that like to eat things around the cell, have receptors that detect the Fc portion that I mentioned before, and when they detect this in a cell, they will engulf it and digest it. And to test this in the lab, we have these beautiful 96-well plates, which is the plastic that Nina was mentioning yesterday. And we put our tumor cells that have GFP. So these cells we can follow by flow cytometry. They're essentially green. We added the therapeutic antibodies and macrophages, of course. And then we incubate for a few hours and we put it in the flow cytometer. And this is what we get. So in GFP, we'll have the tumor cells, and in APC, we have CD11B, which is a marker of macrophages. So here we have the cells that are only tumor cells. Down here, we have the macrophages, but in the middle, we have those macrophages that ate a tumor cell because they're both green and CD11B positive. So we treated a panel of neuroblastoma cell lines with either an irrelevant antibody, anti-GD2, anti-GM2, or a combination of both. If we start with a cell line that doesn't have any GD2, of course, in red, GD2 doesn't do anything. And all the phagocytosis is driven by GM2. We don't have cells that have GD2 but not GM2. So if they have high GD2, they also have GM2. And here we can see that both of them drive phagocytosis. But it's these middle gray areas that have a little bit of each where we see an additive effect of adding both antibodies. The other interesting thing that antibodies do is they interact with NK cells. NK cells are super cool. It's called natural killers because they are like assassins that the body has that just target an objective. And what these NK cells do is they get activated through certain receptors. One of them detects the Fc in the antibodies, and when they do, they kill the cell that is interacting with them. So to see this in the lab, we have a slightly different assay. Of course, we use our green tumor cells and the therapeutic antibody. Now we add NK cells. And then we do a co-culture, so we put both cells together, and in a machine that is called an IncuCyte, which is basically a fluorescent microscopy that is microscope that is inside of a tissue culture incubator. So we can follow the cells in real time because we can see the green of the cells. So if we put an antibody, the cells without antibody, you can see how the curve goes up because the cells are growing, we have more green. If we put an irrelevant antibody, the cells will still grow. But when we put an antibody that actually targets the cell, we can see how the NK cells can kill all the tumors. So again, with our lovely panel of neuroblastoma cell lines, we can see that if the cells don't have GD2, the anti-GD2 doesn't do anything, but the anti-GM2 can drive antibody-dependent cell cytotoxicity. As I said before, all the cells that have GD2 also have GM2, so both antibodies works. And in the middle area, we again see some degree of additive effect. But this is all nice, but it's in plastic. Something more close to reality is the in vivo experiment. So we take these mice that don't have any fully functional immune system, so they cannot reject if we inject them with human tumor cells. However, these mice have macrophages, and that's why we can see some effect of our antibodies. We inject the tumor cells. A few days later, we start measuring the growth of those tumors, and then once we confirm that all the mice have tumor, we start treating with our therapeutic antibody. And then we do some downstream analysis once we have tumors. So in this model, these cells don't have any GD2. They're GD2 completely negative. They're high for GM2. We give them anti-GD2, doesn't do anything in red, but in purple you can see that the anti-GM2 has some effect, but then all the mice relapse. And when we looked at the endpoint at all the tumors that relapse, we don't see any changes, any remodeling, any loss of GM2. On the other hand, if we now take a cell line that has some more GD2, the amount of GD2 that this cell line has is not enough to have some efficacy, but GM2 still works on this line. And here we see the loss of GD2 that we have seen before, right there. And then now we have a cell line that has a lot of GD2 and some GM2, which is what we believe most neuroblastoma look, at least in the beginning. Here we have a modest efficacy of both anti-ganglioside antibodies, but again we have this loss of GD2 that we've seen both by flow cytometry or IHC. Here basically more brown means more GD2. But it's when we combine both anti-GD2 and anti-GM2 in these mice that we can completely eradicate the tumors in mice. But the lab also works on CAR T cells, and you've heard about CAR T cells all the time. Probably you know what they are. I made this slide before I knew that. But basically, the CAR T cells mix the best parts of an antibody with the best parts of a T cell. So the way the T cells recognize their antigen is they need some help. It has to be presented to them in what is called MHC. And what many tumors do is they stop producing MHC, so the T cell then cannot see it. But antibodies don't need MHC. They can see the antigen in its native way in the surface of a cell. So we take the SCFV, the Fab part of the antibody that can recognize the antigen, and we fuse it to the internal machinery of the T cell receptor that activates the T cell. So now, when the antigen is recognized by the antibody part of the receptor, it will activate the T cell and will trigger a response. So we took the binding part of our anti-GM2 antibodies, and we make our GD2 CAR T cells, and we tested them. GM2 CAR T cells, sorry. So this model is really high for GD2. We have some efficacy of the anti-GD2 CAR T cells, but then they relapse. But the anti-GM2 CAR T cells don't do anything. However, you can see that in this case, in purple, the anti-GM2 CAR T cells are putting some pressure on the tumor because they are losing the GM2. And the opposite happens with the anti-GD2 CAR T cells. So since the combination worked so well before, we said, okay, why don't we make a CAR T cell that is able to recognize both GD2 and GM2? So it's the same principle, we just put both parts of the antibody. And when we use these CAR T cells, again, the combination going after both targets completely eliminates the tumors. But with any therapy, there are risks and toxicities, and for those of you that have knowledge of GD2, you know that there is a pain associated that needs to be treated with narcotics, and there are other side effects. So a concern for us was that if the same tissue that has GD2 also has GM2, we may have high toxicity. So what we did is we screened what is called a tissue microarray that has a lot of spots of normal tissue for our gangliosides. And while GD2 was mostly in the central nervous system, so in the brain, in the cerebellum, in the spinal cord, GM2 was mainly in the kidney and the thyroid. So here you can see GD2 is brown in the brain and dorsal root ganglia, and GM2 is mostly in the kidney. But turns out that the mice that we were working with don't have any GM2 in the kidney. There is a different strain of mouse called C57 Black 6 that have it, so we decided to do a toxicity model with these mice. And what's also interesting is that in orange you have a sample of a human kidney, in black is 3 of these mice, and you can see that they have a similar amount of molecules. We can calculate the number of molecules in the lab by flow cytometry. And what is also interesting is that this is CHLA is a cell line that doesn't have a lot of GM2, but still is many orders of magnitude higher the amount of GM2 in the cancer than we have in normal tissue. So this is basically what we did. We took the mice, we treat them with antibodies, we measured the weights, and there was no changes in body weight, also no sign of distress by these animals. There was no pathological features on the kidney of these mice, and also we didn't see any remodeling of the ganglioside that we see on the tumor cells, and these make cells. So the last thing I want to show you is without this fancy IHC and stuff, can we predict which gangliosides are going to have a certain tissue or a certain type of cancer? And this is more broad outside of neuroblastoma. So this was a simplified way, but this is a bit more complicated. But the only important thing here is that we have these upstream enzymes that we need to have present in the cells. Otherwise, we won't have the substrates that we need. And then we have the downstream enzymes that we don't want on the cell because otherwise GD2 or GM2 will be converted into something else. So when we analyze this, so the size of the circle is showing you how much of the upstream enzyme, so you want a big circle, and the color is showing you the expression of the downstream enzyme, so you don't want that to be very bright, let's say. And then we have the amount of the two enzymes necessary to make GD2, so before-garden-1 and ST8SI1. And neuroblastoma is all up there, and it has a lot of the both most important enzymes, and that's why you have so much GD2 and so much GM2. But we found this other disease, LMS, which is not a pediatric cancer, is leiomyosarcoma, which is an adult sarcoma. But since we had available samples, we wanted to test if this was accurate. And while these samples didn't have, or they have a heterogeneous amount of GD2, sorry, they all had GM2. So now we are working on these, which are pediatric cancers. Gliomas are the most common type of brain tumors, and GBM is one of the most aggressive. And we are working on other gangliosides that we can target here, GD2 and GD3. So without, after that, the conclusion is that we can see GD2 loss both in tumors and in models and in patient samples. This is some of a pat in my back because I'm a biologist, so by understanding the biology behind the disease, we found out a new target. We can, to a degree, prevent immune escape by going after both these targets, and that hopefully GM2 is a safe target that we can deploy along with anti-GD2 to treat patients. So I want to thank all the members of the lab that help, or the funding agencies, and of course the patients and their families. And if you have any questions, feel free to ask.
I have a question about the GD2 expression. When it's suppressed, I was just here saying that my son's had a lot of chemoimmunotherapy, and it's starting to not work as well, or maybe at all, we're not sure yet. So I'm kind of curious if we were to find some other ways to help stabilize his disease without anti-GD2 treatments, could the GD2 recover so that perhaps later, could it perhaps recover so that we could use anti-GD2 later? What do you see in that?
Yeah, that's a great question. I can tell you what I see in cell lines, which is nowhere near close to what happens in patients. In cell lines, that's 100% true. If after we take the tumor out of the mouse that has lost GD2 and we put it back in the culture condition, we see GD2 gradually going up. But that doesn't necessarily mean that that will happen in a human being, because one thing that we need to understand about all of this is that there are models, and models have limitations. A petri dish in which the cells are growing at the bottom of a pool covered with nutrients is not the same as the hypoxia that is in the tumor microenvironment, all the other cells. So the short answer is we don't know. But on that regard, if you remember yesterday when Nina was presenting, she was talking about ways of driving GD2 up with epigenetics. And we have done also some experiments like that, and we can drive GD2 up. But yeah, all of these things have to be then properly evaluated in patients.
Anyone else have any questions? Oh, okay, go ahead.
So we're very familiar with drugs that are used to target GD2, and so this is the first time I've heard about potentially targeting GM2. So it sounds like this is only being done on a cellular model or in mice, but it's never been done in humans. Is that correct?
Well, no, I didn't put all that here, but we didn't invent these antibodies. They already existed. They were used in small cell and multiple myeloma, but they didn't have much efficacy in those diseases. So it's been tested in humans, not in neuroblastoma.
Anyone else? That's it? Okay. Thank you, Nico.
Thank you so much.
Thank you. We're actually a little bit ahead of schedule. They may have put the food out in the kitchen for lunch. If it's ready, go ahead and eat. Otherwise, we'll wait until everything gets in there. And we'll be back at about 1:15. So.
have to get this, that's fine.
I can move it.
Tell us where to move. Okay.
GD2, hey, hey.
Okay, we're going to go ahead and get started. Our next speaker is Dr. Meredith Irwin. She's a pediatric oncologist and clinician scientist focused on translational research of neuroblastoma. Her lab studies include identification of signaling pathways involved in cell survival and invasion, and identification of drug targets and therapies through functional screens and tumor sequencing. Her research also involves studies of relapse therapies, including precision medicine approaches, surveillance and genetic screening, predisposition to NB. She's also co-director of the Neuroblastoma program at the Hospital for Sick Children in Toronto, and the chair of the Children's Oncology Group Biology Subcommittee, and member of the COG Neuroblastoma Executive Committee. She leads the COG efforts to modify our neuroblastoma risk classifications, and her talk today is on COG, neuroblastoma biology, and risk classification. Dr. Irwin.
Thanks. Thanks, everybody. It looks like I have 5 minutes and 24 seconds, but I think they're going to hopefully reset that. Thank you so much, Pat and CNCF, for the opportunity to speak with all of you today. Let's see, I should have tried this first. So these were the topics I was thinking of covering. It's slightly more than what I put into the title. So I wanted to give you all a little bit of the framework for how I think we need to think about precision oncology and risk classification for neuroblastoma, and how I think understanding the biology influences how we classify, but also a lot of the questions you all were asking this morning as well. And a little bit of biology biomarker testing 101 now and what we're doing in the future. So one thing I really wanted to highlight, because I often hear people, talk about different doctors in different places and scientists, is that I do think we all really work together globally. And I think we don't just do that because it's the right thing to do, but actually you all know neuroblastoma is a rare tumor, even though it doesn't feel that way today in this room. And that the more we learn about neuroblastoma, there's rarer and rarer subgroups of it. So if we don't work together, we're not going to get far. And as you'll hear, that's how we've gotten to the places that we're at today. So we really do work very well. The slide in the middle is from the Netherlands last month, an international meeting, but really across Europe, Australia, North America, we're always collaborating, the oncologists, the scientists, the patient advocates, and importantly, the patients. And patients have been a critical part of how we've advanced things. And really, before I give you some of the results and some of the things we're thinking moving forward, I want to tell you how we got here and how important patients are, and the data from patients and the specimens and all of the information we get, because every patient that we've been studying is how we've gotten to where we are and how we're going to get farther. So you all know that the Children's Oncology Group is the largest consortium for clinical trials in North America. And one of the ways we've been able to learn about biomarkers is really the focus we've had for the last couple decades on registering all of our patients, getting lots of clinical data and lots of biomarkers and biospecimens, and also with permission of patients and families, storing extra samples so we can keep learning as we discover more things. And that's how we've gotten to where we are with risk classification as well. And then Daniel alluded to the International Neuroblastoma Risk Group task force, and that's a group internationally where we take COG data and data from many of the other clinical trials groups across the world and put that together to really come up with the ability to look at especially very rare subsets and to come up with ways of harmonizing how we think about neuroblastoma and how we risk classify, so we can hopefully start really better comparing across different countries. So I think you all know what biomarkers are, but I have a few definitions just to give you how I think about these things as we talk about them. So the crystal ball is really how I think about biomarkers, because there's been a lot of questions like, what should my child get? What kind of treatment? And really what you're asking is for a little bit of a crystal ball, but I think biomarkers help us have an informed crystal ball. So there's many types, but the three I think we think the most about in neuroblastoma are diagnostic ones, which we're not really going to talk a lot about today, but that would include things like urine catecholamines that help us detect the presence or the type of a tumor. But we're all here with neuroblastoma, so we don't have to think about that. Prognostic biomarkers like MIC-N that give us a clue as to what's going to happen in the future, the likelihood of cure. and survival. And then predictive biomarkers, which I've heard a lot of discussion about how we could find some. And those are really the type of biomarkers that maybe help us identify a treatment that's more or less likely to work for a particular child, and possibly at a particular time point in their trajectory, like an ALK mutation. And there's lots of other types of biomarkers that are very important in cancer, including neuroblastoma, but we're not going to speak about today. So the second definition is precision oncology. And I think that's a lot of what we think about, most especially at relapse, but also at diagnosis. So this slide, which I've borrowed from another group on the internet, is how we think about oncology. And I've tried to adapt this to neuroblastoma. So when patients come in, we know they have neuroblastoma, but we don't know what's different about them all. But when we put together a lot of the clinical factors, age, stage, and different biomarkers, we start to get the sense that patients are different, like that middle part of this slide. And then we hope that as we stratify patients using all of that information, we can come up with different treatments for different patients. Or what we do now, tailoring therapy, although not as precisely as here. And the other thing I want to emphasize is this isn't just about genes and stage of patients, but we actually increasingly think there's other factors that influence how patients will respond. And at SickKids, where Daniel and I work, we have a tagline our CEO coined, from the postal code to the genetic code, just trying to encompass, it's a lot of features that go into how we treat our patients. So I learn a lot by history, and I think it's really important to look at how we've gotten to where we are so that we make sure we continue to make progress. And I'm sure most of you know who Dr. Audrey Evans is. We refer to her as the mother of neuroblastoma, but she really was the first person to publish, at least, thinking about neuroblastoma as a precision medicine type of disease. And this is a copy of a pile of her index cards from Peter Adamson, who worked more closely with Audrey, and he lent me this after I saw him use it in a talk. And what this is a pile of cards, and Audrey felt that the patients she saw, some of them resembled each other and some didn't, based on their clinical features. And she started to recognize that that was also associated with the patients who survived versus those that didn't. And she wrote this up because that's what we all do when we make, an observation. And this really turned out to be the first staging system in 1971, named for Dr. Evans as the Evans staging system. And I quoted a few lines from that paper, which really is a harbinger for how we think about classifying patients today. A staging system was proposed to aid in estimating the prognosis and evaluate the efficacy of different regimens by analyzing results in comparable groups of patients. Basically, clinical trials with risk stratified patients in 1971 is what she proposed. You may all know there's a movie about her. I highly recommend it. If you haven't seen it, it's streaming. And I don't know if you all know that she was also the co-founder of the Ronald McDonald House, which is among many of the other impressive things that she did. So when I think about neuroblastoma, and this is a slide I use actually when I have given talks to our residents and our fellows, I think of it again as the spectrum. This probably is close, but not exactly, to Audrey's index cards. On the left are the patients who often are young, who come in with very small tumors, maybe even are born with them, or livers that in babies are covered with neuroblastoma and do fine either with surgery or observation, versus those all the way on the other side, like many patients, I think, who many of you have in your families, who often have resistant metastatic disease or disease that comes back many times. And then those in the middle that are somewhere in between that often can be cured with some chemotherapy and or surgery. But what we know now is, even though a lot of this is about these clinical features I just described to you, a lot is about the biology, and we're getting more and more precise by using biology, and that's how we've gotten a bit farther than the index cards, but still room to go. So if I sort of make my own slide, like that first one I showed you, before Dr. Evans and her colleagues thought about risk classification, all the patients were really being treated the same, which was mostly surgery back then and a little bit of chemotherapy. But now with the biomarkers that we're using currently that are listed below, we have these three buckets you hear about, low, intermediate, and high. But what do we do now to get to the next level, to really get those multicolor, individualized predictions for patients, both in the beginning at diagnosis, but also later? And this is just the slide which many of you would be familiar with of the outcomes for those different groups of patients on a traditional Kaplan-Meier, which I think you've looked at many of at this conference and others, where the low and intermediate risk patients do very well, 8 to 9 out of 10 survive, whereas high-risk patients still, despite all the progress, are 5 to 6 out of 10 surviving. So again, there's these biomarkers, but what I want to show you, and I think this is actually, again, the power of this data that we have from all the patients we've had the privilege to study over the years. This is thousands of patients in the INRG. If you look at age and forget about everything else, their stage or McN or anything else, age alone is prognostic. So when we know the age of a patient, we already have an inkling of how it's going to go. Of course, stage, metastatic in red or not metastatic, very important. We use a different staging system now, but this is older data. And then things like how it looks under the microscope, how proliferative it is, or the histology is very important, and McN, of course, which I've already heard a few of you ask about or talk about today. I'm going to mention McN because I know most of you are familiar with it, but I actually think we're maybe at going to be at a little bit of an inflection point where maybe we can do something about it. So it's a gene that's known in the lab for actually about 3 decades now to control cell growth and many other important pro-cancer pathways. You probably all know this, but we do a test called FISH, shown on the bottom, and we use these fluorescent probes. You should only, in most normal cells, have 2 copies, like in red, which is a normal non-McN gene. But if you have more than 4, and often neuroblastoma tumors that are amplified have hundreds of these McN genes, there's a poor prognosis associated with that, regardless of everything else about the patient, the stage, et cetera. But what's exciting now, I think, but still I think several years away, is there is some progress in the lab of figuring out how we might be able to finally drug McN, not quite like ALK, but maybe some other ways of fooling McN and lowering McN's activity in the cell. So I think that is a few years away, but I think it is something we should look out for with some new techniques for drugs, something called degraders and some other things like that. So we take all these risk factors, we put them into this complicated algorithm, and then we figure out what risk group a patient is when they come in the door. We're also doing this internationally, and we're trying to update that. So this is great for diagnosis, and this is great for sort of where we were in the last decade, but where are we going to go now, and how are we going to get to sort of this more precision group? And I think we're really, again, with all of the new techniques in sequencing that I'm going to talk about, and data and AI, hopefully we're going to get to the point where we can really start, just moving faster than we have been able to move, where we look at one gene at a time, et cetera, in the past. So one of the ways we get there, you've heard me talk about biomarkers. How do we get all these biomarkers? We have to really be thoughtful when we do a trial, and this is kind of my schema of high-risk therapy, not too dissimilar to what Daniel showed you with a little more detail of the 3 phases at most centers in North America, and trying to get samples at multiple time points and especially diagnosis so that even if we don't know what to look for now, as we get results of our studies, we can go back and understand why that treatment worked or didn't work, or at least try to. So at diagnosis, as you all know, we get lots of samples from the tumor, from the bone marrow, and increasingly more samples from the blood or other samples of so-called normal cells. And these are really important, as I said, both now to be able to look at biomarkers, but also as we learn more and more to go back. And I want to talk about a concept that I've heard come up sort of in the background so far that's really important to biomarker discovery. So in the past, I would say we thought of the tumor like the one on the left, where the cells were pretty similar, maybe slightly different shades of the same cell, but mostly the same genes, the same mutations. What we know now, and again, we've talked a little bit about this, is that a tumor is actually a bunch of heterogeneous different cells. So even when we look at those FISH, those beautiful fluorescent slides of neuroblastoma, some cells have 100 copies of McN, some have 10, some have 2 in the same tumor. So that's a clue that they're not all the same. And so the different colors are meant to represent that. And what we also know is as you treat a tumor, or when a tumor comes back, some of the cells go away and some new ones, like the purple cells, show up. And so that might mean there's some new mutations that are appearing over time. So this is not only interesting, but also makes things a bit complicated. So this is my schema showing that, if you now are an interventional radiologist or a surgeon and you're taking a biopsy of that tumor, depending on where you take that sample, you may get very different samples. And then in addition to all these different tumor cells, there's some little blue cells in there that are meant to be immune cells, which we just heard about earlier today, how important those cells are, especially with how important immune therapy now is in our regimens. So we are using these samples now for the pathologist to help diagnose the tumor and to test all those biomarkers like McCann. And we're also using these samples now to learn what's different about all those cells. And critically important work, including by Pat Reynolds, who presented to you all this morning, trying to make cell lines and to make tumors in the lab from the extra samples has really helped us get to where we are today, and I think will continue to tell us more and more. And we now know these cells can actually even change in real time how they express different genes and mutations. So that all sounds very complicated. What's the future? And again, I heard this mentioned briefly, liquid biopsy. So tumor cells, we know, get shed into the bloodstream, and no surprise, neuroblastoma, with the burden of disease that we see, has some of the highest levels of this of any pediatric or adult tumor. And what we think is really an unprecedented opportunity is that all of these different cells may shed. So instead of worrying, did I get the needle in the right place, maybe you get a representative population, at least of the most frequent, so more maybe of the pink cells than the purple cells, but that may help us in the long run. And I'll show you at the end a study that I think will give us a lot of insight in the next year, hopefully, about that. I'm going to talk briefly just about chromosome copy number alterations. I think this isn't really going to have that much influence on treatment, so I'm going to go through this a little quickly. But just to say, in the past and currently, we do use some of the copy number changes as a prognostic marker, and that's because in all of our cells, we should have 23 pairs of chromosomes, and those should be full chromosomes. But in neuroblastoma, we know there's a lot of extra pieces and lost pieces, and we know some of those actually are prognostic. So shown here on the right is what's called a segmental loss of chromosome 11q, where you can see just a little piece is missing there where the arrow is. And we know that if you're missing a little piece of certain chromosomes, including 1p and 11q, that is associated with a worse prognosis. In contrast, if you gain or lose like a whole chromosome, so you just have lots of copies of 11 or chromosome 2 or 4, that is probably not the same problem as gaining or losing just a little itty-bitty piece. So just mentioning that because that does come up sometimes, but I think it's less relevant moving forward to how we think about different treatments, because you lose or gain a lot of different genes, and I'm not sure that we're able to target all of those. I think mutations are going to be much more informative. So that gets me to where are we going with biomarkers, like what's just about ready for prime time, what's going to help us risk classify better, and what helps us with drug targets. So a couple of areas that I think we really need help from diagnosis but beyond is better biomarkers to tell us which of the patients we have with high-risk disease is ultimately going to recur. So we're not waiting to figure that out. Who isn't going to respond to the upfront therapies that we're giving? Maybe those are patients who should go on a different trial or a different arm. And then one of the things that troubles a lot of us is we have this amazing survival for intermediate risk and high risk and low and intermediate risk patients, but every so often there's a patient who slides through and we just got it wrong and they recur and basically become high risk. So if we could find those, as I call them, needles in the haystack, patients who really are, a little bit blue and not that red intermediate, could we find those patients earlier and treat them as high risk from the start? And then the predictive biomarkers that we all need way more of, the ones that help us understand if targeted therapies to ALK, is there an ALK mutation? Is there another mutation that will make my child respond to a very specific drug? Immunotherapies, you heard about all these exciting immunotherapies for GD2. Lots of the kids who many of you have in your families have gotten GD2, either dinutuximab or some CAR-Ts. Understanding what are the biomarkers, maybe GD2 is one of them, but are there other biomarkers that tell us who are the 50% of patients that respond to chemoimmuno and who are the ones that are going to respond again? We really don't know. And then which therapies for which patients. So those predictive biomarkers, I think, are still elusive outside of ALK mutations, as Daniel said this morning. So these are some of the things we're doing to try to get better biomarkers. We've already talked a bit about sequencing, but I'll give you my sort of view of that. Looking more at the genes that actually get expressed after the DNA encodes those mutations. The telomerase pathway you heard a bit about from Pat, I'll just show one slide, and then immune cells as well. So there's lots going on in the cell, but the sort of three basic things are the DNA that encodes all of the genes, so that's those different base pairs where we look for those one or two mutations that might change everything, lead to a different RNA and a different protein. Proteins are at the end, the things that carry out the jobs. So basically make a protein like a GD2 that sits on the end of the surface of the cell and allows the cell to respond, hopefully, to dinutuximab. There's other things at the surface, or what's called the surfaceome now, that we're looking at to see if we can target those with new immune therapies, especially for children who don't respond to GD2. And then proteins are things like ALK and other enzymes that activate pathways and potentially make cells more and more tumorigenic. So when we talk about sequencing and the tumor and potentially the liquid biopsy or the blood, I think it's, the old way was one gene at a time, but when you hear about sequencing and when a few people have talked to me about sequencing, it's important to know not all sequencing is the same. So I think many of you know this, not every sequencing test you get will tell you the same information. So the whole exome is the genes that get expressed and make genes. The whole genome is much bigger, and it's a lot more information. And then panels, which many people get, tend to be narrower, so much smaller if you go all the way from the apple to the slice to like a tiny bite of the apple. But sometimes that has the ability to look very deep or very sensitively at a very small number of genes. So that can be very helpful if you know you're following 2 or 3 genes and they're on that panel. You might get more bang for your buck, but if you don't actually know what you're looking for or your panel is negative, it may mean you need a more broad approach. And I'll also say that some of the panels that are made by, I'd say, more adult-centric companies or hospitals may or may not have all the genes we care about in neuroblastoma. So it's important to know what's on a sequencing test before knowing how to interpret those results. I think I'll skip that in the interest of time. So we've been very lucky with some generous funding from the NCI at COG to be able to do upfront sequencing. So when patients if they are enrolled on this MCI, Molecular Characterization Initiative at COG, we actually, within 2 to 3 weeks of getting the tumor at Nationwide, in the lab of Elaine Martis, we're able to actually do a full exome sequencing right at diagnosis, giving not just the MICAN and ALK and copy number, but a whole list of other potentially actionable genes now or in the future. And we've now done this on about 600 patients up front, mostly high risk, but a few intermediate risk. And I don't have to tell all of you that ALK is the most common mutation, but on the right is just a schematic of the 3 hotspots and a bunch of others mutations, just to highlight the fact that not every ALK mutation is created equal. Not every ALK mutation responds the same to lorlatinib or to the newer generation ALK inhibitors, so we know that sometimes one ALK inhibitor may work better for one mutation than another, and sometimes we don't even know that until we try it in our patients. As you know, we're testing that up front in 1531 for patients we know at diagnosis from the MCI have an ALK mutation. And then there's many other mutations, and again, as we talked about with the purple cell coming up over time, those can change over time. Daniel mentioned RAS inhibitors. We're very excited. Our lab and others have shown a lot of really nice responses in cells that have some sort of RAS abnormality in that pathway, and that's the drug that's worked really well in pancreatic cancer, or at least on some patients with pancreatic cancer with RAS abnormalities. And then there's a whole host of other mutations, including ATRX that Dr. Reynolds talked about, and more rare ones like FGFR1, which is very, very rare, but there are drugs. There'll probably never be a trial, but it is important to know. And then there's many others. But these are tiny, tiny groups of patients. And then again, I think Dr. Reynolds spoke about telomerase. All I will say is I know he spoke about some very specific studies, but I think Telomerase itself and maintaining these very long telomeres is how a cancer cell kind of keeps living. It's sort of immortal, basically, never ages the way a normal cell ages. And so the cell figures out many ways to do that, not just in neuroblastoma, but especially in neuroblastoma, and it includes that alt type of abnormality that he spoke about. And what's important about that is it does seem to pick out patients that don't do as well, but I think what's going to be more exciting in the future is there may be drugs that will work on these types of neuroblastoma. We don't have them yet, but there's a lot of work looking for those. So again, important to pick out those patients. And as Pat showed, there may be patients with that abnormality that do or don't respond as well to transplant. So maybe that'll give us a clue moving forward on the study Daniel described to think about, is that something that will help us understand who will or won't benefit from a transplant? And finally, some of this was discussed in the last talk before lunch, GD2. We need to be measuring GD2 routinely, which we're doing on our current high-risk COG study. And we can do that on the tumor, the marrow, and we think maybe in the blood and serum. So that's all happening as we enroll patients on 2131. And our questions on that trial, with a group of patients all being treated the same, with or without immunotherapy, is, does it actually predict? It seems like it should, but we still don't have data that proves that the level of GD2 correlates with the response to dinutuximab and ultimately CAR-T, which is, something else that we're going to be looking at that in Europe they have a lot more experience with. And then, again, I think you heard a little bit about this yesterday, drugs that may help increase the level of GD2. And finally, the liquid biopsy is super exciting, not just because many of us do not want to retire still doing bone marrows, but I think because it is a way to get lots and lots of sequential samples now that we know how smart neuroblastoma is, outsmarting us and changing all the time. So this is a simple blood draw that many of your kids have had, but could this replace a tumor biopsy? I think that's really the question. I would say today, pretty easy to say not completely, but I think if a child doesn't have something that can be biopsied, especially at relapse, it's the right thing to try to get. And Daniel has a study that we're trying to enroll patients specifically who can't get a biopsy and see if that could substitute for it. Again, Daniel spoke a little bit about the crystal ball possibilities for ctDNA. So of course we could sequence genes either at the same time we're biopsying a tumor or potentially multiple other times along the way. It will have the ability, I believe, to give us MIC-N data. We know it can show us the copy number of many genes, including MIC-N. It does have the potential to as a monitoring biomarker. And the other thing it's really been shown to be powerful is patients on different types of drugs, and especially in lung and other types of cancer in adults, we can actually see mutations that are resistance mutations develop before our eyes. So I think that ultimately we can't act on that because we don't know all of that yet, but that will eventually help us figure out early maybe when a drug's not working anymore, like an ALK inhibitor. So within the next year, you heard we're going to hear the results of this COG 1531 trial that's looking at MIBG therapy, but what's really exciting is we have ctDNA samples on these patients from, I think it's 10 or 12 time points up to, depending on if we collected all of those. And at most points, we also have imaging, not at every point, but many. So I think what we're going to learn from this trial, and these are the questions we're addressing, is will ctDNA be equivalent to tumor sequencing? We also have tumor sequencing on these patients. We already know from preliminary data that sometimes we see things in the tumor we don't see in the ctDNA, and vice versa. So it's definitely telling us it's heterogeneous, and for now, maybe both are helpful, at least at diagnosis. But does the burden, so how high the level of ctDNA is, predict recurrence, and does it predict recurrence before the scans, which is what we really want to figure out. And then in complementary work done by our colleagues in Europe, they have a trial, they always have really better names than us, called Mona Lisa. It's a long name, but it's about cell-free DNA. I don't remember what it all stands for. But essentially, they're doing a trial in relapse patients where they're comparing the ctDNA results to the scans. They're also embedding patient-reported outcomes to try to understand how families feel about doing yet another study. And of course, that may depend on if they get a result or not, but I think it's really important to also be asking those questions at the same time we're looking at the results and see how how that affects not just the treatment the patients get, but people's experiences. And the exciting thing in Europe is they can do this in multiple countries and multiple populations, and we'll get a lot of data from that. And finally, we haven't spent a lot of time talking about sort of predictive biomarkers for late effects, but we all know the high-risk therapy we give has many, many late effects, and this is a slide I modified from my friend Lisa Diller, who's really an expert in late effects and led this powerful study, really the first large study of late effects in high-risk neuroblastoma, which are laid out here. And now there's a study pending with funding from Gabriela Miller Kids First, looking at the genomics of these patients to see if, looking retrospectively now, there are any biomarkers that we could start thinking about up front that would have helped us predict which patients will have ototoxicity, which patients maybe will have a second malignancy. And I think this will be a really powerful study. I'm sure we're going to have to validate the results, but it's really exciting. And finally, though it's not a classic biomarker, I think increasingly we're learning that the social determinants are things like poverty that patients grow up in and experience during their treatment does impact on the outcome, as well as other disparities, including racial disparities. And it's important for many reasons, but if you look at this Kaplan-Meier curve, it's not a gene like McN, it's poverty. And the reason I say it's important is these differences are not that different from some of the biomarkers I showed you. So if you don't look at this, but you just look at biomarkers, you're missing part of the picture. So this is definitely something else I think we really have to think about. And obviously it gets to access not just for upfront trials, but for relapse therapies and other things. And we see this even in Canada, where we have public health insurance, because there's still difficulty, navigating around the country to get to different centers. So I think the big challenge, and all this is meant to show you, is there's just so much information we're getting now, and it's at a rapid rate like never before. And if you add in things like digital histology that I know you heard Mark Applebaum talk about, and he's doing a ton of great work with a lot of the same samples we've already studied, Curie scores, all the information in our electronic health record like EPIC, social determinants using AI, I think our risk classification schema are going to start being almost like three-dimensional. And hopefully we'll also start to get to the point where we can figure out more biomarkers at relapse that will help us, not just the first relapse, but later, but especially at the first relapse when we really want to make that first decision. Is it a chemoimmunotherapy? Is it something else? How can we predict that first therapy that we're going to recommend for a patient? And so in conclusion, this is actually one of our patients, a patient of mine for almost a decade and a half, who was probably on the most clinical trials of any of our patients in our neuroblastoma program, and also inspired a lot of work in the lab where she visited with her science class. And I think was just a really inspirational. I have many inspirational patients, but I think as I think about precision oncology, this was probably one of the first who made me think a little differently about what we were going to do in the lab to change how we attack this problem. So really it's evolved over 50 years, and I think we're making increasing progress now, but using the same paradigms, just trying to get smarter with the new technologies. And I think we continue to use biomarkers with our clinical acumen and the clinical features to determine risk groups and tailor therapy, especially at relapse when there's a lot less, there's fewer and fewer patients in each group and a lot less experience. I think we do have to work together, and many of us do, to make sure we're getting the best information for our patients. And then I think the future, both from tumors and ctDNA, are going to help us get even smarter at how we optimize all of these decisions. And so for me, I just want to thank our patients and the patients of all of these cooperative groups that have led to all of this work, and all of you for listening. And I'm sure many of you have also contributed biospecimens and consent for studies, which is how we learn. And a quote from one of my colleagues, and I hope I can consider friends, Leona Knox from Solving Kids Cancer, who herself is a neuroblastoma expert. She said to me and to a group when she gave a talk after many of us had spoken about precision oncology, that for families, despite all these biomarkers, the true nature of their child's disease is really only revealed over time, which I think is really what I have learned, taking care of so many, having the privilege to take care of so many patients and families. So I'm happy to take questions, and these are lots of the people who've helped do all of this, and they're all fair and unfair. I heard you say a lot about unfair questions, so anything is on for this.
Thank you, Dr. Irwin. If few people standing up already? Okay.
Okay, great.
Hi, I'm Andrew. How do you feel about epigenetic biomarkers and ctDNA? That's been a big topic right now, and it just seems like a broader net to cast to be able to look across the entire genome and look at all the epigenetic marks. So what's your feeling, or how do you think that's going?
So I don't know if he spoke about it yesterday, but Mark Applebaum, who I think spoke to you more about digital histology, I think, yesterday. But he's also on that same study, 1531, where we're doing kind of more classic sequencing. He's also, from the samples that had enough extra, because you have to prepare it slightly different, he's also doing some methylation studies on some of those, epigenetic studies. So I think, and we're seeing some different things and some similar things. So, and I also think he has done some of that, although not published yet, on some of the NANT trials to compare to some of the other types of minimum residual disease type testing that the NANT group has done, and seeing if they're complementary or one is better than the other. So I definitely think so. And I think from a discovery, to your point, it is quite broad. I think we'll get a lot more information from that. And we do have, on a research basis, methylation data on the tumors on the MCI, those 600 tumors. So I think if we can compare that, that will also give us a lot of information to base what we see on the cell-free. So yeah, I think it's really important. I mean, we would love to do everything. We try to draw, enough blood, but not so much blood from all the kids. So thank you.
Thank you. Go ahead.
The social determinants of outcome are huge numbers in terms of the difference. Looks like 35%. And the other question is was that Canada or the U.S. or?
So most of that data was from the U.S. because they looked at things like insurance, which for us, everyone has at least baseline, although drugs aren't free, and all drugs aren't free in Canada. But I do believe, we haven't studied it in detail, but I do believe we see it. It's probably for us more due to other factors besides insurance, but we do see material hardship. Also in that same study, when they looked at material hardship independent of insurance or Medicaid, they did see some differences based on parental income and things like that.
That was like a 35% spread.
It's pretty high, yeah.
In the U.S., it's been 25. I mean, before.
It is pretty high. And if you think about all the traveling a lot of people do to get access to different therapies, I mean, that was just an upfront trial, so that's not one of the variables. But obviously for some families, that's really difficult to be able to do. So we always have to think about that too when we're looking at trials, that the population is not always reflective of all of the patients that it's one of the good things about COG. There is access, throughout, but that's only upfront, not for relapse. But I think it's super important. We do believe, and I'm not speaking for myself, but Kiribona and others who did that work, that it probably does, there are changes to the biology actually when you undergo stress, various types of stress, or different diets, et cetera. So they are doing some work to also look at the immune microenvironment and how that appears to vary in different racial backgrounds and under different stresses. The racial background part's a little harder right now with some of the funding issues, but some of the rest hopefully will be very informative. So I think it is linked to the biology. It's the other reason I include it. I don't think it's just having that. I think it does something different to the immune system or something.
And there's a heavy-duty psychological portion of this as well.
For sure.
Thank you.
Sure, thanks.
Thank you. One more. Go ahead.
I have two questions. The first one is, you talked about the difference between a biopsy and then a liquid biopsy, and how they're not exactly equal. It would be nice if we could do a biopsy, get more information. As a parent, I don't know that I always want there to be
100%.
a biopsy. So I was wondering if you could speak about that a little bit, like the risks inherent in an actual biopsy. And then my second question is very different, and you might be able to just remember them both and go on.
So that's good. Thank you so much for giving me the opportunity to answer the first one. So when I said at the same time, I think we still think at diagnosis, we're not ready to get rid of the biopsy, because all of our data that we would give you as parents is based on the tumor information. And so the curves, the sort of how we decide what we do. I think after that, we're going to get to the point when we have this comparative data from 1531 and a few other studies, like from our Europeans, where we wouldn't do as frequent of a tumor biopsy. Now, bone marrow could be in between. You know, we don't sequence bone marrow that much. We've had some experience in MCI, where if we have enough tumor cells, usually only at diagnosis, we can actually get a lot of the rich sequencing data that we get from the tumor cells in the bone marrow. So there may be an in-between there, at least at diagnosis, and we've sent ourselves bone marrows to sequence when we can't get, it's a necrotic tumor, or it's too dangerous to get enough sample or something. So I agree. I mean, I think you heard me say I don't even want to be doing bone marrow biopsies anymore if I can, you know, if we can get this all to work out eventually. But I think at the diagnosis, we're not ready to get rid of the biopsy unless it's dangerous. You know, it's definitely risk-benefit ratio. And then I think we do think about sending in a diagnosis if it's too risky to biopsy. But I totally agree about the risks.
Oh, good.
100%. And I don't want to be doing them all the time.
I'm really happy to hear that, actually.
Yeah.
My second question had to do with the picture of your patient that you had on there and how she really inspired you and your staff. And I'm wondering, what was so inspiring that you started thinking about all of these targeted therapies that she could receive? Like, how can we inspire our doctors, like, well, so that we get all those targeted therapies too? Like, what was so inspiring?
So Daniel and I work together, and we're a team. You know, I'm like, have the lab, which he worked in for a while, but decided he belonged more on the clinical side, and I do both. But essentially, I would say it inspired me to also change my direction in the lab a little bit from what I would describe as very basic science to this more translational. So she was one of the first patients on our sequencing study at SickKids when we started that 11 or 12 years ago now. And we found some things that were unusual, which now we wouldn't call as unusual, but at the time, not ALK, other things. And as she started not responding to other therapies as much, we started asking, is there something we could do? So at the same time that Daniel was searching for things to try that maybe worked in adult tumors that had similar mutations, we wanted to model some of these genes in the lab, and that's what inspired me to kind of change what we were doing. We started working with not just mice, but zebrafish, and tried to make that same. We'd love to get cells like I showed you, but often it's really hard to get the cells to grow from every patient and every biopsy. So we tried to mimic those. And so it took us on a whole different direction in the lab and trying to model these things in fish and cells and sort of taking what we learned from the patient. And it didn't work always in real time for her, but she also would be and I was like, you do? Okay, like we could do another biopsy. So I think it was that type of a thing, and her interest in trying new therapies, but she always balanced that with her like wanting to drive, wanting to go to this event, wanting to go on this vacation, so we tried to make it work, basically. But I think she just inspired me to think a little differently, and I saw, you know, that she did have relapse disease for a long time. I think these things contributed to a longer duration of her life, but it's hard to know for sure.
One more question.
Sorry, I talked.
Oh, no, that's okay. That's okay. If we can do 2 quick questions, hopefully.
Okay. I'll give quick answers.
Okay. I know for us and probably many people, we, had basically no idea anything was wrong with our child till the tumor was so big, and then bam, you have a cancer diagnosis. And so my question from the beginning was like, had we have had our urine markers, would that have tipped us to think something was wrong with her earlier, younger? Or had she had a random screening, and I think like of newborn screens, and we do like regular screenings on kids at age 1.
To screen, we might, as all these other technologies work, they're looking at the little blood spots in leukemia and other diseases where I think there'll be much bigger numbers to try to figure this out. So I think this is one time where we probably have to follow leukemia a little bit.
And that's a little bit different with like smears and things like that.
I think the first thing will be using this more to predict recurrence, or maybe even on a trial to predict a progression before an MIBG.
Okay, thanks.
Okay, go ahead. One question.
Hi, I think it's really interesting that you touched on the social determinants, which gets really close to exposure to environmental toxins. My daughter was born with 4S, diagnosed on day 1 of life, and the oncologist at Detroit Children's told me that it was likely due to my exposure to pesticides while pregnant. Like that was her understanding. And in the 3 years since that, I have looked at different articles, and of course I see that there's differing opinions on that. So I was just hoping that you could touch on that.
Sure. I would say when I've looked at this as part of writing reviews, and also Daniel and I wrote something for the Canadian Cancer Society for parents and families, we could not find any statistically data that showed that association. I think other than genetic predisposition, I don't think we've found anything at this point that we really believe predisposes toxin-wise or environmental exposure-wise to neuroblastoma. And there were studies looking at folate years ago, different things. I don't think any of that has panned out in a way that I believe it to be true. And there are people who've looked at it with way more expertise than me, and those are the papers that I've looked at.
Didn't Andy Olshan do a lot of epidemiology studies?
I think they do have more things going on now.
Yeah.
There's an epidemiology group at the COG who collaborates with the disease groups, and I know with a lot of this germline sequencing through that Gabriella Miller group that's doing it for the late effects, they also have other projects, and that is the group, to Pat's point, that's probably the most expert. They have not put out anything on exposures being positive yet for neuroblastoma. But I know it's something people wonder, especially with a disease that disproportionately affects newborns and infants compared to other age groups, for sure.
Okay. Thank you, Dr. Irwin. Appreciate it. Our next speaker is Joy Grigsby. She brings 27